Welcome to the story of time. For the next 3 hours, we're going to journey through one of humanity's greatest obsessions and deepest mysteries: time. You experience it constantly. It moves through you and around you. You feel it passing, measure it, fear its loss, and dream of having more of it. And yet, if asked to explain what time actually is, most of us would struggle. Because time might be the most fundamental mystery in all of science and philosophy. In this exploration, we'll begin where humans always begin, with wonder. We'll travel from ancient civilizations watching the sky, through the minds of brilliant thinkers who dared to question what everyone assumed was obvious, into the laboratories where scientists discovered that time itself is far stranger than we ever imagined. We'll explore how time shapes consciousness, culture, and meaning. And we'll confront the deepest questions. Does time really exist? Can it be stopped? Does it flow backward? And most importantly, what does time mean for a life like yours? Finite and precious, and burning against the infinite dark. So settle in. This is a journey meant to be experienced slowly, to be listened to and contemplated. If you're finding this helpful, please like and subscribe to the channel. It helps us reach others who are curious about the profound stories hidden within science. And if something moves you, share your thoughts in the comments. We'd love to hear what time means to you. Now, let's begin. The philosophical puzzle. The ancient Greeks were perhaps the first to ask, what is time, really? And in asking, they discovered something that every thoughtful person discovers when they try to think clearly about time. It is very difficult to say. Around 500 BCE, a philosopher named Heraclitus proposed something radical. Everything flows. The world is not a collection of fixed, unchanging things. Rather, reality is process. Change is fundamental. You cannot step in the same river twice, he said, because the river is always flowing, always new. And if everything is always changing, then change and time are the same thing. Reality is the flow of time. But Heraclitus had a contemporary named Parmenides who disagreed profoundly. Parmenides argued that change is an illusion. True reality, he insisted, must be unchanging and eternal. If something comes into being or passes away, that means at some point it did not exist or ceased to exist. But true being cannot come from non-being. Therefore, change is impossible. Therefore, time, if time is the measure of change, is impossible. Reality is static, eternal, unchanged. Between these two ancient thinkers, we find the fundamental tension that would occupy Western thought for millennia. Is time real, or is it an illusion? Is change fundamental or illusory? Heraclitus said yes. Time is the very nature of reality. Parmenides said no. Time is a trick. Our senses play on us. Centuries later, Zeno of Elea, a student of Parmenides, created a series of paradoxes designed to prove that motion and time are logically impossible. His most famous paradox concerns Achilles, the swift runner, racing a tortoise. Imagine Achilles gives the tortoise a head start. To overtake it, Achilles must first cover the distance the tortoise has already traveled. But in the time, Achilles covers the distance. The tortoise moves further ahead. Achilles must now close that new distance. But again, the tortoise moves ahead in the time it takes. This process repeats infinitely. Therefore, logically, Achilles can never catch the tortoise. And yet in reality, of course, Achilles catches the tortoise easily. So we have a paradox. Reason tells us motion is impossible, but experience tells us motion happens. Zeno's paradoxes troubled philosophers for over 2,000 years because they revealed something deep. Time and space are not as obviously simple as they seem. There is something subtle about infinity, about the division of space and time into smaller and smaller pieces, about the relationship between discrete moments and continuous flow. These are not primitive confusions. These are genuine philosophical problems. Nearly 2,000 years after Zeno, Augustine of Hippo confronted the problem of time with particular poignancy. Augustine was deeply personal in his philosophy. He did not ask what is time in the abstract, but what is time for me, a conscious being, living and dying. And he wrote, "What is time? If no one asks me, I know what it is. But if they ask me, and I try to explain, I find I cannot." This is perhaps the most honest statement ever written about time. Augustine understood that time is intimately known and utterly mysterious. We live in it constantly. We cannot imagine existing outside it. And yet the moment we try to define it, it slips from our grasp like water through our fingers. Augustine proposed that time exists primarily in the mind. The past exists as memory. The future exists as anticipation. The present exists as the immediate experience of the moment. But these three dimensions, memory, perception, anticipation, all occur in the consciousness of a single person. Time, then, is not an external thing. It is the structure of consciousness itself. This was a profound insight. It suggested that time and mind are inseparable. You cannot have time without a mind to experience it. But it raised another puzzle. If time is in the mind, what accounts for the objective regularities we observe? The sun rises and sets whether or not anyone is watching. Stars appear in the same positions year after year. If time is subjective, how can nature operate with such mechanical precision? These ancient questions, posed by Heraclitus and Parmenides and Zeno and Augustine, are still with us. We still do not have a final answer to the question, what is time? We have better theories, more powerful descriptions, deeper insights. But the fundamental mystery remains. And perhaps, as Augustine suggested, this is not a failure of understanding. Perhaps time is one of those phenomena that can be known completely only by surrendering the demand for logical explanation. Perhaps time is something to be lived and contemplated, not fully solved. Eastern perspectives. While Greek philosophers in the Mediterranean world were wrestling with time as a linear problem, in other parts of the world, different visions of time were developing. These visions were not less sophisticated. They were differently sophisticated. In Hindu philosophy, particularly in texts like the Rig Veda and the Bhagavad Gita, time was understood as cyclical. The universe moves through vast ages called yugas, from the golden age to progressively darker ages, until the cycle completes and begins again. A day of Brahma, the creator god, lasts billions of human years. And then Brahma sleeps, and the entire cosmos dissolves and is reborn. This is not time as a line moving from past to future. It is time as a circle, eternally returning. Creation and dissolution, birth and death, are not events that happen once. They are the eternal pattern of existence. Within this cyclical vision, individual lives take on different meanings. Your life is not a unique journey from birth to death and into nothingness. It is one turning of an infinite wheel. You have lived before. You will live again. The goal of spiritual practice is to step outside this wheel, to escape time altogether through enlightenment. Similarly, in Buddhist philosophy, time is understood as dependent on consciousness. Without a mind to perceive it, time does not exist. All phenomena are impermanent, constantly arising and passing away. Nothing lasts. All is flux. But unlike Heraclitus, who saw this as the fundamental nature of reality, Buddhism sees this impermanence as a kind of suffering, a condition to be understood and transcended. In Taoism, particularly in the writings of Zhuangzi, time appears as something to flow with rather than to master. The Tao, the way, is the natural flow of the universe. To live well is to align yourself with this flow, not to fight against it with schedules and plans. There is a kind of timelessness in perfect alignment with the Tao, a state where you forget yourself and simply act naturally, without the friction of thought. These Eastern philosophies share something that distinguishes them from much Western thought. They do not assume that time is something out there, that exists independently of consciousness and perception. Rather, time and mind, time and reality, are deeply interwoven. Change the consciousness of the observer, and the experience of time changes. The cyclical vision of time in Eastern traditions also suggests something different about meaning and purpose. If time is linear, as Western tradition tends to assume, then history has direction. There is a beginning, a middle, and an end. Events have an order and significance relative to that narrative arc. But if time is cyclical, then meaning is found not in progress toward a distant goal, but in harmony with eternal patterns. Neither view is more true than the other. They are different ways of relating to the fundamental human experience of temporal passage. And here is what is worth noting. These different conceptions of time shaped entire civilizations. In cultures with a linear conception of time, there is often an emphasis on progress, on improving the future, on long-term planning. In cultures with a cyclical conception, there is often an emphasis on maintaining harmony with patterns, on seasonal rhythms, on the eternal recurrence of meaning. Western science eventually adopted a linear, directional view of time. The universe had a beginning, develops according to laws of physics, and may have an end. This has profound implications for how we live and what we believe matters. But the Eastern perspectives, which have persisted for thousands of years, remind us that other ways of relating to time are possible. They suggest that our Western scientific view, for all its power and precision, captures only one way of understanding something as fundamental and mysterious as time itself. Perhaps the deepest wisdom about time comes not from choosing between linear and cyclical, between Western and Eastern, but in recognizing that time might be more vast and multifaceted than any single perspective can encompass. Shadow and water. For thousands of years, humans marked time by the most obvious instrument available, the sun. But obvious does not mean simple. To harness the sun's movement as a tool for measuring time required observation, mathematics, and a willingness to translate the heavens into something tangible and useful. The sundial represents one of humanity's most elegant technologies. The principle is simple. A shadow cast by the sun's position reveals the hour. But the execution demanded precision. The gnomon, the part that casts the shadow, must be positioned at exactly the latitude where it is used. The surface must be marked with hour lines calculated through geometry. And the whole instrument assumes that you are observing the sun on a clear day at a single location. The earliest sundials appear in Egypt around 1500 BCE, though there is evidence of simpler sun tracking methods centuries before. The Egyptians understood something crucial. Time could be made visible. The sun's position could be encoded onto stone or wood. A person could read the time not by feeling the passage of duration, but by observing where a shadow fell. This was revolutionary. It meant that time was no longer purely internal, a matter of bodily sensation and personal perception. Time had become external, observable, objective. But sundials had limitations. They did not work at night. They did not work on cloudy days. They could not be carried with you. And so humans invented another approach, water clocks or clepsydras. These appear in Egypt around 1500 BCE as well, and they persist through Greek, Roman, and Islamic civilizations for millennia. A water clock is elegant in its simplicity. Water flows at a constant rate from one container to another. Markings on the receiving container show how much time has passed. The constancy of water's flow, dependent on gravity and the size of the opening through which it flows, creates a steady measure of duration. Unlike the sundial, the water clock works day and night, in clear weather and fog. A water clock can be enclosed in a building. It can measure time independent of external circumstances. It is, in a sense, the first portable, reliable time measurement technology. The Islamic world developed water clocks to extraordinary sophistication. The Abbasid engineers of Baghdad in the 9th century created mechanical water clocks of stunning complexity, with gears and escapements and astrolabes, combining hydraulics with mechanical precision. These were not mere practical tools. They were demonstrations of human ingenuity, ways of making the invisible visible and bringing order to the chaos of temporal experience. Alongside water clocks came hourglasses, or sand clocks. A measured amount of sand flows through a narrow opening from one bulb to another. When all the sand has fallen, a specific interval has passed. Hourglasses are cruder than water clocks. The size of sand particles affects the flow rate, but they are portable and require no external power. A person could carry an hourglass and measure time wherever they went. These three technologies, the sundial, the water clock, the hourglass, represent humanity's first systematic efforts to quantify time. And they share something important. They are all based on observation of natural processes that flow at constant rates. The sun's motion, water's gravity-driven flow, sand's descent through an opening. By carefully observing and measuring these processes, humans learned to read time as if it were written in the world around them. But there was still a problem. These instruments could measure intervals of time, but they required constant attention and interpretation. Someone had to read the sundial, watch the water level, flip the hourglass. Time was becoming measurable, but not yet automatic, not yet mechanical. That would require one more leap of imagination. Mechanical time awakens. The invention of the mechanical clock represents a turning point in human history, more profound than most people realize. It is not simply the invention of a better timepiece. It is the externalization and mechanization of time itself. It marks the moment when humanity decided that time was not something to be experienced, but something to be controlled. The earliest mechanical clocks appear in Europe during the 13th century. They were powered by falling weights and regulated by mechanisms that allowed the weights to fall at a steady rate. The key innovation was the escapement, a device that allows energy to be released in small, regular increments rather than all at once. With an escapement mechanism, time could be divided into discrete, uniform units. The clock's bell would strike to mark the hours, and the rhythmic ticking sound became the heartbeat of the medieval city. The monastery was perhaps the crucial site for the development of the mechanical clock. Monastic life was structured by prayer at specific times throughout the day: matins at midnight, lauds at dawn, prime at first light, terce at mid-morning, sext at noon, none in the afternoon, vespers at sunset, and compline before bed. These were the canonical hours, and they had to be observed with precision. The water clocks and hourglasses of antiquity were not precise enough for this demanding schedule. A mechanical clock that could ring a bell on schedule would free the monks from the burden of constantly watching for the right moment. And so, monastic communities across Europe invested in mechanical clocks. Bells tolled through the night to summon monks to prayer in the darkness. The sound of the clock became the orchestrating principle of monastic life. Time was no longer something you experienced subjectively. It was something imposed from outside, measured in uniform intervals, announced by the community's clock. But something unexpected happened. As monasteries became more precise with their clocks, they began to notice something odd. The clocks themselves were not precise. Different clocks ran at different rates. Some were faster, some slower. Time itself, as measured by mechanical instruments, turned out to be variable. This troubling discovery led to one of the most important moments in the history of timekeeping. In 1581, according to the famous story, the young Galileo Galilei was sitting in the cathedral in Pisa, watching an oil lamp swing back and forth after being lit. He timed the oscillations using his own pulse as a reference. Whether or not this specific story is true, Galileo made a crucial observation. A pendulum, swinging back and forth, takes the same amount of time for each oscillation, whether the amplitude is large or small. The period of a pendulum's swing is independent of how far it swings. This is called isochronism, and it is the key to precision timekeeping. If you could attach an escapement mechanism to a swinging pendulum, the pendulum's natural rhythm would regulate the release of energy, creating a clock of unprecedented accuracy. Galileo proposed this idea but never built it. It was left to Christiaan Huygens, a Dutch mathematician and physicist, to actually construct the first pendulum clock in 1656. Huygens' clock was revolutionary. With a pendulum regulating its escapement, it could maintain accuracy to within a few minutes per day, a dramatic improvement over all previous timekeeping technology. And Huygens understood the significance. He was not simply inventing a better clock. He was harnessing a fundamental law of nature, the constant period of a pendulum's swing, and using it to impose regularity on time itself. The pendulum clock spread rapidly through Europe. As these clocks became more common and more accurate, something subtle began to shift in human consciousness. Time was no longer something you felt or experienced. Time was something that could be measured, recorded, compared, and synchronized. If two pendulum clocks were set correctly, they would agree about what time it was. If your clock disagreed with another person's clock, one of you was wrong. Time had become objective, standardized, external. This was profoundly powerful and profoundly alienating. The mechanical clock made precision possible. It allowed for unprecedented coordination of human activity. It enabled the development of commerce, science, and centralized government. But it also severed the connection between time and human experience. You no longer asked how much of the day remains until sunset. You asked, what time is it? And the answer came not from your own perception or bodily sensation, but from an external mechanical authority. The precision age begins. The pendulum clock was a breakthrough, but it still had limitations. Pendulums are sensitive to temperature changes, which affect the length of the metal, and thus the period of oscillation. They are sensitive to vibration and movement. A ship tossing in the ocean cannot maintain accurate time with a pendulum clock, which is why the problem of finding longitude at sea remained one of the great unsolved challenges of the age of exploration. Throughout the 17th and 18th centuries, brilliant minds worked on improving timekeeping. They developed escapement mechanisms of increasing sophistication. They created clocks with multiple pendulums compensating for temperature variations. They miniaturized the technology until pocket watches were possible, time you could carry with you at all times. John Harrison, an English horologist, spent decades developing a series of marine chronometers, finally creating a clock that could maintain accuracy across months at sea. His H4 chronometer, completed in 1759, could determine longitude with unprecedented precision. This solved one of the great practical problems of the age, but it also reflected something deeper: the obsession with precision, with measurement, with the quantification of something that had never been quantified before. By the 19th century, the atomic structure of matter was beginning to be understood. Scientists realized that matter vibrates at specific frequencies, that atoms have characteristic oscillations. The idea arose, why not use an atom's natural vibration as the regulator for a clock? The vibration of an atom is far more regular than a pendulum's swing. It is not affected by temperature or vibration or gravity. An atomic clock could be vastly more accurate than any mechanical clock. The cesium atom became the standard. In 1967, the international scientific community officially defined the second as the duration of 9,192,600,000 1770 cycles of radiation, corresponding to the transition between two energy levels of the cesium-133 atom. The second, which had once been a simple division of the day into 24 times 60 times 60 equal parts, was now defined by the quantum vibration of an atom. Time had become atomic. Modern atomic clocks are accurate to within 1 second in several million years. They can measure time to billionths of a second. They are so precise that Einstein's theories of relativity must be accounted for. A clock at higher altitude, farther from Earth's gravity, actually ticks slightly faster than a clock at lower altitude. The differences are tiny, fractions of a nanosecond, but at the precision of atomic clocks, these differences are measurable and real. We have now reached a point where we can measure time with such precision that we must account for the curvature of space-time itself. We measure not just duration, but the way gravity and motion affect the very flow of time. The journey from the sun's shadow to atomic oscillations represents a profound shift in human knowledge and power. We have learned to measure time with ever-increasing precision. We have learned to synchronize global timekeeping to unprecedented accuracy. And in learning to measure time so precisely, we have discovered something unexpected. Time itself is not as simple as we thought. At the most fundamental levels, time is affected by gravity, by motion, by the quantum nature of reality. The quest to measure time has become the key to understanding the deepest nature of reality itself. When trains changed everything, imagine a world with no standard time. In the 19th century, before the railroad, this was normal. Each town kept its own local time, based on the position of the sun at noon. If the sun was at its highest point in your location, it was noon in your town. A town 50 miles east would have a sun at its highest point a few minutes earlier. A town 50 miles west would reach noon a few minutes later. This variation was negligible for most human purposes. If you traveled by horse or carriage, the time differences were minor compared to the length of the journey. But in the 1830s, the railroad changed everything. Suddenly, you could travel 50 miles in an hour. If you left town A at what its clock said was 2 p.m. and arrived in town B an hour later, what time was it in town? Was it 3 p.m. according to town B's local time, which had reached 3 p.m. some minutes earlier due to the sun's position? Or was it 3 p.m. according to when you left? The confusion was more than academic. Railroad accidents began to occur because timetables could not be standardized. A train leaving Boston at 2 p.m. Boston time would arrive in New York at a time that depended on whether you calculated using Boston time or New York time or something in between. Collisions happened. People died. The railroad companies realized that they needed a solution. In 1883, the railroad companies of North America made a radical decision. They would divide the continent into 4 time zones. All clocks within a time zone would be set to the same time, regardless of the actual position of the sun. This was the birth of standard time. It was not a decision made by governments or scientists. It was made by railroad companies solving a practical problem. But its implications were vast. For the first time in human history, a region of the Earth was divided by artificial, arbitrary time boundaries. It did not matter that the sun reached its highest point at different times in Boston and New York. They would keep the same time anyway. The synchronized clock had replaced the sun as the reference point for time itself. Other countries adopted similar systems. Britain established Greenwich Mean Time as the international standard. By the early 20th century, most of the world was organized into time zones, all coordinated to a single reference point, the meridian passing through Greenwich, England. This was an extraordinary assertion of human will over natural phenomena. The position of the sun determined time no longer. Instead, an arbitrary convention, a human agreement, determined time. And this convention was made not for philosophical reasons, but for the prosaic purpose of running trains on schedule. Yet consider the profound implications. Time was no longer something natural and variable. Time was something standardized and imposed. If you traveled from Boston to New York, you did not experience the gradual change of the sun's position that your ancestors would have known. Instead, you suddenly found yourself in a place where the clocks said a different time, even though the sun was in the same position in the sky. Your body, tuned to the actual position of the sun, would gradually adjust over days. This is the phenomenon we now call jet lag, though it is really just the lag of your body's circadian rhythms catching up with the clocks in the new time zone. The railroad and standardized time also had profound effects on labor and capitalism. With standardized time, factory schedules could be imposed with precision. Workers did not begin and end their shifts based on natural cues or their own sense of fatigue. They began and ended based on the clock. Time became a commodity. You could waste time or use time well. You could be on time or late. Time became something that could be bought and sold. An hour of your labor had a monetary value, and that value was determined by external measurement, not by the value of what you produced or how you felt about your work. Standardized time was essential for the Industrial Revolution, but it also marked a kind of loss. The human experience of time, which had been cyclical and natural, becoming more linear and mechanical. The present, which had been something you inhabited and experienced, becoming something you located on a timeline marked by external clocks. This transition happened gradually, but by the 20th century it was complete. Humans in industrialized societies lived primarily in clock time, not natural time. The implications would take decades to fully emerge. But the seeds were planted in the 1880s, when railroad companies decided that the sun's position did not matter. What mattered was the synchronized agreement of clocks across vast distances. What mattered was coordination, precision, control. Atomic precision and beyond. As the 20th century progressed, the demand for ever greater precision in timekeeping intensified. The development of radio and later television and telecommunications required synchronized signals with unprecedented accuracy. If two signals were even microseconds out of synchronization, they would distort each other. The pendulum and quartz clocks of the early 20th century were not precise enough. The answer came from quantum mechanics. In 1945, Isidore Rabi, an American physicist, demonstrated that atoms could be used as frequency standards. When atoms transition between different energy states, they emit or absorb radiation at very specific frequencies. These frequencies are determined by the laws of quantum mechanics and are fundamental properties of the atoms themselves. Unlike mechanical oscillations, which depend on physical construction and are affected by temperature and vibration, atomic transitions are intrinsic properties of matter. They are the same everywhere in the universe. The cesium atom, in particular, has a transition frequency that is extraordinarily stable. In 1955, Louis Essen and Jack Parry at the National Physical Laboratory in England built the first practical cesium atomic clock. It worked by taking cesium atoms and measuring the frequency at which they transitioned between two specific energy states. By counting the cycles of this radiation, one could measure time with extraordinary precision. The cesium clock was immediately adopted as the new standard for timekeeping. Its stability was so superior to mechanical clocks that it made previous standards obsolete. More importantly, the cesium clock could be synchronized globally. Every cesium clock, anywhere in the world, would measure the same frequencies. This meant that precise global synchronization became possible for the first time in human history. In 1967, the International System of Units officially redefined the second. No longer was the second defined as a fraction of the Earth's rotation or a fraction of the solar day. Instead, the second was defined as 9,192,631,1770 cycles of the cesium-133 radiation. Time itself had become atomic. When you look at your phone and it displays a time accurate to a millisecond, you are looking at a derivative of atomic time. GPS satellites maintain cesium clocks and transmit time signals accurate to billionths of a second. These signals are used to synchronize financial transactions, power grids, and communications networks across the globe. Modern atomic clocks have become even more precise. Optical lattice clocks, which use multiple atoms held in place by laser beams, can now measure time to better than 1 second in 15 billion years. They are so sensitive that they can detect the slight changes in gravitational field caused by changes in elevation of a few centimeters. They can measure the relativistic effects of Einstein's general relativity. The human obsession with measuring time has led us to instruments so precise that they reveal the fundamental nature of space-time itself. We have traveled from sundials that mark the hours to atomic clocks that measure the vibrations of quantum particles. We have moved from time as something experienced naturally to time as something defined by the deepest laws of physics. And in this process, something unexpected happened. The quest to measure time revealed that time itself is far stranger and more wonderful than anyone had imagined. The road from shadow to atom is a road that led us to the very heart of reality. Newton's absolute time. On a winter's day in 1642, Isaac Newton was born in a small village in England. The year Galileo died. By the time Newton reached his 20s, he had access to a new kind of mathematics, calculus, and a new way of thinking about nature. During the plague years of 1665 and 1666, while Cambridge University was closed and he retreated to his home, Newton worked on the problems that would occupy his entire life. How does the universe work? What are the laws that govern motion and force? How can we describe the behavior of objects, from falling apples to orbiting planets, with mathematical precision? Newton's answer, published in his Principia Mathematica in 1687, was revolutionary. He proposed 3 laws of motion and a law of universal gravitation, and he grounded these laws in a conception of time that seemed so obvious, so natural, that it would go unquestioned for over 200 years. Newton defined time as absolute. In his own words, absolute, true, and mathematical time, of itself, and from its own nature, flows equably without regard to anything external. This was a profound assertion. Time, according to Newton, is not something that changes from place to place, or that depends on what is happening in the universe. Time is universal, uniform, and independent. It flows at the same rate everywhere. 2 observers in different places, moving at different speeds, watching different events, will still agree on the duration of time between any 2 events. This seems obvious to us now, because we are so accustomed to synchronized clocks and standardized time. But Newton was making a deep, philosophical claim. He was saying that time is a fundamental feature of the universe, independent of motion, independent of matter, independent of anything that happens within time. It is the stage upon which all of physics plays out. With this conception of absolute time, Newton could write his equations of motion. An object at rest stays at rest, an object in motion stays in motion unless acted upon by a force. Force equals mass times acceleration. These laws, expressed mathematically in terms of positions and velocities and accelerations over time, could describe the motion of everything from projectiles to planets, and they worked. Newton's equations predicted the orbits of planets with extraordinary accuracy. They explained the tides, the precession of the equinoxes, the behavior of comets. For the first time, human mathematical thought could describe the actual motion of celestial bodies. The success was intoxicating. Here was proof that the universe operated according to mathematical laws. Here was the promise that if we only knew the position and velocity of every particle in the universe, we could calculate everything that would happen forever. The universe was a great machine, and time was the dimension in which this machine operated. Newton's absolute time became the foundation of physics for centuries. It fit with everyday experience. Clocks agreed with each other. A second was a second everywhere. Everyone could agree on the order of events. This happened before that, which happened before the other thing. Causality flowed forward in time. Effects followed causes. The universe seemed to move according to a logical narrative, with time as the thread that tied events together. But there was something strange lurking in Newton's formulation. If time flows equably without regard to anything external, then what is time actually made of? What is the substance of this thing that flows? Newton never answered this question satisfactorily. The absolute time he described was abstract and mathematical, useful for calculations, but strange when you tried to imagine it as a real thing. Critics pointed out the oddity. Leibniz, a contemporary of Newton, argued that time is not an absolute thing but relational. Time is the order of successive events. You cannot measure time independently of what is happening. The very idea of absolute time, flowing independently of anything, is incoherent. But Leibniz's criticism, though philosophically sophisticated, could not match the practical success of Newton's framework. His equations worked. They predicted, they explained, they enabled the development of technology. And so Newton's absolute time became, by default, the standard view. It would take 200 years and a peculiar problem with light before anyone seriously questioned whether Newton was right. The Clockwork Universe. Newton's laws, combined with the conception of absolute time, gave rise to a vision of the universe that became dominant in the 18th and 19th centuries, the mechanistic universe. The idea was simple and profound. The universe is like a great clock. It has been wound up at the beginning, and now it ticks along according to mechanical laws. Everything that happens is the result of these laws acting on the initial conditions. If you knew the position and velocity of every particle in the universe at some moment in the past, you could, in principle, calculate everything that would happen in the future. This vision had enormous appeal. It seemed to offer complete understanding. It suggested that the universe is rational, orderly, comprehensible. There were no mysteries, only calculations we had not yet performed. It also had profound philosophical implications. It suggested that the future was already determined. If the present state of the universe uniquely determines the future, then the future is fixed. What will happen is already decided. The only question is whether we can calculate it. This deterministic vision troubled some thinkers. What about human freedom? If the future is already determined by the laws of physics, how can human choices be free? How can you be responsible for your actions if they were determined centuries ago by the initial state of the atoms in your body? The most famous response came from Pierre-Simon Laplace, the great French mathematician and astronomer. Laplace imagined an intellect vast enough to know the position and velocity of every atom in the universe. Such an intellect could, he argued, calculate the entire past and the entire future. This is the thought experiment now known as Laplace's demon. Laplace himself did not think Laplace's demon was actually possible. Human knowledge was limited. We could never gather enough information to predict everything. But he was making a point. Given Newton's laws and absolute time, the universe is, in principle, completely predictable. The future is fixed. We simply lack the knowledge and computational power to see it. This deterministic worldview became entrenched in 19th century physics. It seemed to follow logically from Newton's laws and the nature of absolute time. Everything that would ever happen was already implicit in the initial conditions of the universe. Time was not creative. Time did not generate novelty. Time was merely the dimension along which predetermined events unfolded. But alongside this mechanical vision, something else was happening. The development of thermodynamics, the science of heat and energy, was revealing something that did not fit neatly into the mechanical picture. Thermodynamics suggested that time had a direction. It suggested that the universe was not a perfectly reversible machine, but something that had an inherent direction of change. This was the discovery that would crack the foundation of Newtonian determinism, though not in the way most physicists expected. Heat and the arrow of time. Imagine a glass of hot water placed on a table. You observe what happens next. The water cools down. The heat spreads out into the room. Eventually, the water reaches room temperature. Now imagine the reverse. You place a glass of room temperature water on a table, and you observe that it spontaneously becomes hotter, with the heat drawn in from the surrounding air. You have never seen this happen. You will never see this happen. It violates no law of Newton's mechanics. The atoms of the water could, in principle, spontaneously organize themselves into a hotter state, while the air around them becomes cooler. The molecular motions that constitute heat could, in principle, reverse themselves. But we know from universal experience that this does not happen. Heat always flows from hot to cold, never from cold to hot. Temperature differences always tend to even out. Disorder always increases. This observation, formalized into the laws of thermodynamics, revealed something profound about the nature of time. The first law of thermodynamics is conservation of energy. Energy cannot be created or destroyed, only transformed from one form to another. This law has no direction. You could run the universe backward, and energy would still be conserved. But the second law of thermodynamics says something different. The entropy of an isolated system always increases. Entropy is a measure of disorder, or more precisely, the number of microscopic states consistent with a given macroscopic description. A glass of hot water has lower entropy than the same water when it has cooled down, because the hot water has more organized, directed molecular motion. When it cools, that organized motion becomes random thermal motion, and the entropy increases. This second law is asymmetric. It has a direction. It says that systems naturally evolve from ordered to disordered states, and this gives time a direction. The past is the state of lower entropy. The future is the state of higher entropy. Time flows from order to disorder. This was a puzzle for 19th century physicists. How could this asymmetry arise from Newton's laws, which are themselves symmetric in time? If you reverse the velocities of all particles in a system, Newton's laws would run backward perfectly. A movie of molecules following Newton's laws could be played in reverse, and the laws would still be satisfied. Yet the second law of thermodynamics clearly has a direction. Disorder increases. How can this be? The answer comes from probability and statistics. James Clerk Maxwell and Ludwig Boltzmann worked on this problem and came to a realization. The second law is not absolute. It is statistical. Given any particular arrangement of molecules, there are many more arrangements that are disordered than arrangements that are highly ordered. So if you start with an ordered state, the system will almost certainly evolve toward disorder simply because there are so many more disordered states available. It is not that disorder is impossible. It is that disorder is vastly more probable. The arrow of time, then, comes from probability. The future is the direction of higher entropy, because that is the overwhelmingly probable direction. If you were to wait an incomprehensibly long time, you might see a glass of room temperature water spontaneously become hot. But the waiting time would be longer than the age of the universe by an incomprehensible factor. This resolution seemed to many physicists unsatisfying. It made the arrow of time a matter of statistics rather than something fundamental. It suggested that the universe's direction was not built into its structure, but arose only from the initial conditions and the laws of probability. And yet, there was something profound here. The second law of thermodynamics offered the only way to distinguish past from future in the laws of physics. Without entropy, without disorder, there would be no difference between past and future. time would be truly reversible. The fact that disorder increases gives time its direction, gives history its arrow, gives the universe its story. We, conscious beings, exist because the universe is far from equilibrium. We are structures of extraordinary order, concentrations of low entropy. We can only exist in a universe that is constantly generating entropy, constantly moving toward disorder. We are, in a sense, passengers on the arrow of time, our very existence dependent on the second law of thermodynamics. This realization was not widely appreciated in the 19th century. Physicists were more troubled by the apparent contradiction between the reversibility of Newton's laws and the irreversibility of thermodynamic processes. This tension would persist, and it would eventually play a role in one of the greatest revolutions in the history of science: the speed of light. By the late 19th century, physicists believed they understood the fundamental structure of reality. Newton's laws governed motion. Maxwell's equations governed electromagnetism. Light was understood as waves traveling through a medium called the ether, an invisible substance that filled all of space. The ether was necessary because waves, everyone knew, must travel through a medium. Sound waves travel through air or water. Ocean waves travel through water. So light waves must travel through something. That something was the ether. But there was a problem. If the ether existed and light traveled through it, then observers moving at different speeds relative to the ether should measure light at different speeds. Imagine you are on a train, moving forward at 50 miles per hour. A ball is thrown forward on the train at 30 miles per hour. Relative to the ground, the ball moves at 80 miles per hour. The speeds add. This is the Galilean relativity that Newton had taken for granted. Velocities are relative. They add and subtract depending on the observer's motion. But in the 1880s, two American physicists named Albert Michelson and Edward Morley performed an experiment designed to measure the Earth's motion through the ether. They used an interferometer, a device that splits a light beam and sends it in two perpendicular directions, then recombines the beams to see if they are in phase. If the Earth were moving through the ether, the two beams should recombine slightly out of phase, having traveled at different speeds through the ether. The experiment was performed with extraordinary precision, and the result was shocking. There was no difference. The speed of light was the same in both directions. The Michelson-Morley experiment was repeated many times by many experimenters with increasingly sensitive equipment. The result was always the same. The speed of light is constant. This was deeply troubling. It violated the principle of Galilean relativity. How could light always travel at the same speed, regardless of the observer's motion? How could the speed of light be 300,000 kilometers per second, whether you are moving toward a light source or away from it? It seemed to violate basic logic. Physicists proposed increasingly elaborate theories to explain this anomaly. Perhaps the ether was being dragged along with the Earth. Perhaps there was a contraction of physical matter in the direction of motion. Perhaps there was something special about the reference frame in which the ether is at rest. But all of these explanations seemed ad hoc, clumsy, unsatisfying. There was a sense among physicists that something fundamental was not being understood. Something about the nature of light, or space, or time, or all three together, was not fitting into the framework that Newton had provided. By the 1890s, the great physicist Ludwig Boltzmann was heard to say that the second law of thermodynamics was just a matter of probability, and electromagnetism seemed to be breaking the symmetries of mechanics. There seemed to be contradictions and mysteries at the heart of physics. In 1900, Lord Kelvin declared that physics was essentially complete, with only a few small clouds on the horizon. Those clouds, it would turn out, contained thunderstorms of transformative power. One of those clouds was the constancy of light speed. Another was the problem of radiation from hot bodies. A third was the behavior of atoms. These problems would lead to two revolutions: Einstein's special and general relativity, and Planck and Bohr's quantum mechanics. These revolutions would shatter the Newtonian worldview completely. They would reveal that time is not absolute, not uniform, not what Newton thought it was. They would show that the universe is far stranger, far more wonderful, and far more mysterious than the clockwork mechanism of the 19th century had suggested. But first, a young patent clerk in Switzerland would have to ask a simple question. What if the speed of light is really constant? What if Maxwell's equations are more fundamental than Newton's? What if we need to abandon the idea of absolute time? The young Einstein. Albert Einstein was born in Germany in 1879. He was a restless student, impatient with rigid education systems, drawn to physics and mathematics. By age 16, he was already thinking about fundamental problems. What would it be like to ride on a beam of light? How fast would the light beam appear to be traveling if you were moving alongside it at nearly the same speed? These seem like whimsical thought experiments, the kind of thing a clever boy might play with in his imagination. But they were actually profound questions about the nature of light and speed and observation. In 1896, Einstein entered the Polytechnic in Zurich to study physics. He was an intelligent student, but not exceptional. He was more interested in understanding physics at the deepest level than in the technical details of measurement and experiment. After graduation, he struggled to find an academic position. His dismissive attitude toward authority and his unconventional thinking made him unpopular with his professors. In 1902, through a friend's intervention, he obtained a position at the Swiss Patent Office in Bern. It was not glamorous. It was not what he had hoped for. But it turned out to be ideal. The work was not demanding. He had time to think. And free from the pressures of academic politics and the need to publish on someone else's schedule, Einstein could pursue his own line of inquiry. In 1905, Einstein was 26 years old. That year, while working at the patent office and thinking about the problems that troubled 19th century physics, he wrote 4 papers. Any one of these papers would have established him as a major physicist. Together, they revolutionized physics. The first paper was on the photoelectric effect. Light hitting metal causes electrons to be ejected. Einstein proposed that light consists of discrete packets of energy, which we now call photons. This was radical because it suggested that light was not purely a wave, as Maxwell had described, but also had particle properties. The second paper was on Brownian motion, the random jiggling of particles suspended in a fluid. Einstein's explanation provided confirmation of the atomic theory of matter, which was still not universally accepted. The third paper was on special relativity. The fourth was the famous equation EMC, which relates energy and mass. The special relativity paper is the one that concerns us now. In it, Einstein took the constancy of light speed seriously, not as an anomaly to be explained away, not as a sign that something was missing, but as a fundamental postulate. He proposed that the laws of physics are the same in all inertial reference frames, and that the speed of light is the same for all observers, regardless of their motion. From these 2 simple postulates, extraordinary consequences followed. Time is not absolute. Simultaneity is not absolute. Moving clocks run slow. Moving objects contract in the direction of motion. Mass and energy are interchangeable. Everything that seemed certain about the nature of time and space had to be reconsidered. Einstein did not have a dramatic insight that came all at once. Rather, he had been thinking about these problems for years. He had been bothered by the apparent contradiction between Galilean relativity and the constancy of light speed. He had been reading the work of other physicists, Lorentz, Poincaré, who had developed mathematical tools that could handle these problems. And he had the intellectual courage to follow the logic wherever it led, even when it contradicted the Newtonian worldview that had been accepted for 2 centuries. In 1905, Einstein published these ideas in a paper titled, simply, On the Electrodynamics of Moving Bodies. The paper was not long. It was not filled with complex mathematics, but it was a complete reconceptualization of space and time. And it was correct. In the years that followed, Einstein would extend these ideas. In 1915, he published his general theory of relativity, which reconceived gravity not as a force, but as the curvature of space-time itself. But in 1905, working alone at the patent office, he had already shattered Newton's absolute time. He had shown that time is relative, dependent on motion and gravity. He had shown that past and future are not universal categories, but depend on the observer's reference frame. He had opened a door to a new understanding of the universe. And most importantly, he had shown that the deepest mysteries of physics, mysteries that had troubled the greatest minds of the 19th century, could be resolved not by adding complexity, but by reconsidering the foundations. The answer was not in explaining away the constancy of light. The answer was in accepting it and allowing it to revolutionize our understanding of space, time, and the nature of reality itself. Special relativity's strange mirror. Einstein's insight began with a simple question: what if the speed of light is truly constant? Not approximately constant, but exactly constant for all observers, regardless of their motion. If this is true, then something must give. Something must change. And what changes is time itself. Consider a thought experiment. You are on a train moving very fast, say half the speed of light. A light beam is emitted from the front of the train. How fast is this light beam traveling relative to you? According to Galilean relativity, which was Newton's assumption, the light should be traveling at the speed of light, minus the speed of the train. If light travels at 300,000 kilometers per second, and the train travels at 150,000 kilometers per second, the relative speed should be 150,000 kilometers per second. But this is not what actually happens. When you measure the speed of the light beam from inside the train, you measure it traveling at the full speed of light, 300,000 kilometers per second. The presence of the train's motion does not slow down the light relative to you. This seems impossible. Velocities should add and subtract. That is how motion works. But light does not obey this rule. Light travels at the same speed for all observers. Einstein took this as his bedrock assumption. From it, everything else follows. If light speed is constant and velocities do not add and subtract in the usual way, then time and space must be relative. They must adjust to maintain light's constancy. Here is where it gets strange. Imagine two events. A light beam is emitted from the front of the train, and it reaches the back of the train. From the perspective of someone on the train, these two events happen at the same location, the location of the light receiver at the back. But from the perspective of someone standing beside the track, watching the train pass, these two events happen at different locations. The light is emitted from the front of the train, then travels toward the back of the moving train, catching up to it. The spatial distance between these events is different for the two observers. Now, here is the crucial realization. If the spatial separation between events changes depending on the observer's motion, and if light speed must remain constant, then the time interval between events must also change. The two observers will measure different amounts of time between the emission and reception of the light. They will disagree about how long the light took to travel, and they will both be right. There is no absolute time that one observer is measuring correctly while the other is wrong. Time is relative. This is not a matter of clocks being inaccurate or observers being careless. This is a fundamental feature of reality. Two observers moving relative to each other will experience time differently. They will measure different durations for the same events. They will disagree about the simultaneity of events. If two events happen at the same time according to one observer, they may happen at different times, according to another observer. The order of events is not absolute. The temporal distance between events is not absolute. Only the speed of light is absolute. Einstein formalized this with the concept of the space-time interval, an invariant quantity that is the same for all observers. The space-time interval involves both spatial distance and temporal distance combined in a specific way. It is the one thing that all observers agree on, even though they disagree about the space and time components separately. This is profoundly disorienting when you first encounter it. It seems to violate basic logic. How can time be different for different observers? How can events be simultaneous for one observer, but not simultaneous for another? But the mathematics is rigorous, and the experiments confirm it. Time is relative. And the stranger thing is, once you accept this, it makes a strange kind of sense. Newton's absolute time seems like the anomaly. How could time be the same everywhere, independent of motion, independent of gravity? Why should the universe care about a universal time? It does not. The universe cares about the speed of light. And in order for light to travel at the same speed for all observers, time must be relative. Time dilation. If time is relative, then here is a consequence. Moving clocks run slow. This is called time dilation. It sounds like science fiction, but it is measurable reality. Here is how it works. Imagine a clock aboard a spaceship traveling at near the speed of light. The clock ticks at regular intervals. Someone on the spaceship measures the time between ticks and finds it normal, 1 second per tick. But an observer on Earth, watching the spaceship pass, measures the same clock and finds that the time between ticks is longer. The moving clock is running slow. From the Earth observer's perspective, the spaceship's clock has slowed down by a factor called gamma, which increases as the spaceship's speed approaches the speed of light. At low speeds, the effect is tiny. A plane, flying around the world at 500 miles per hour, experiences time dilation. But the effect is on the order of billionths of a second. You would have to have atomic clocks accurate to nanoseconds to measure it. But at speeds approaching light speed, the effect becomes dramatic. At 99% of light speed, gamma is about 7. An astronaut traveling at this speed would age 1 year for every 7 years that pass on Earth. At 99.9% of light speed, gamma is about 22. The astronaut would age 1 year for every 22 years on Earth. And as the speed approaches the speed of light, gamma approaches infinity. Time would slow down more and more. The asymmetry is important. The astronaut ages slowly relative to Earth. But from the astronaut's perspective, Earth is moving at high speed, and it is Earth's clocks that are running slow. Both perspectives are valid in their own reference frames. This is the principle of relativity. All inertial reference frames are equivalent. There is no absolute standard of motion. The astronaut is stationary in her own reference frame, and Earth is moving away. From her perspective, people on Earth are aging slowly. This seems paradoxical. If both observers think the other's clock is running slow, how can time dilation be real? This is the famous twin paradox. Imagine two twins. One stays on Earth, one travels on a spaceship to a distant star and back at near light speed. From the traveling twin's perspective, the Earth is moving away and then returning. From the Earth twin's perspective, the spaceship is moving away and then returning. So both twins should age slowly, right? But they cannot both be younger than the other when they reunite. This seems impossible. The resolution comes from the fact that the two twins are not in equivalent reference frames. The traveling twin must accelerate, decelerate, and then reverse course to return to Earth. This acceleration breaks the symmetry. The traveling twin is the one whose clock actually runs slow. When the twins reunite, the traveling twin is younger. This is not a matter of perspective or interpretation. It is an objective fact. The traveling twin has aged less. This has been experimentally confirmed many times. Muons are unstable particles created when cosmic rays hit Earth's atmosphere. They decay in about 2/millionths of a second. Without relativistic effects, muons created at high altitude should decay before reaching Earth's surface. But they do reach the surface. Why? Because they are moving at near the speed of light. From the muon's perspective, time is dilated, and they decay more slowly. From Earth's perspective, the muons are contracted, and the journey is shorter. Either way, the muons reach the surface, confirming time dilation. Atomic clocks have also confirmed time dilation. An atomic clock flown on a fast jet plane runs slower than an identical clock left on Earth. The difference is tiny, but measurable. GPS satellites also confirm time dilation. Satellites orbiting Earth at high speed experience time dilation. Without accounting for this effect, GPS would accumulate errors of kilometers per day. But when the relativistic time dilation is accounted for, GPS is accurate to meters. Time dilation is not a theoretical curiosity. It is a practical reality that must be accounted for in technologies that we depend on. Moving clocks run slow. This is not an illusion or a trick. It is the way time actually works. Time flows at different rates in different reference frames. And there is no universal clock ticking at the same rate everywhere. Each observer carries their own proper time, and for observers in relative motion, these times progress at different rates. Space and time become one. As Einstein developed special relativity, he realized that space and time are not separate things. They are woven together into a unified fabric called spacetime. This insight came partly from the mathematics and partly from deep reflection on the nature of measurement. To measure a spatial distance, you need a clock. To measure a time interval, you need a ruler. Space and time are fundamentally interconnected in the act of measurement. A German mathematician named Hermann Minkowski, who had been one of Einstein's teachers, saw the deep geometric structure underlying special relativity. Minkowski showed that spacetime is a four-dimensional continuum in which space and time are woven together. You cannot change time without changing space, and you cannot change space without changing time. Just as a rotation in ordinary space changes which direction is east and which is north, a change in reference frame, a boost to a different velocity, changes which parts of space-time point in the time direction and which point in the spatial directions. Minkowski described this with a famous phrase, "Space and time are shadows of a deeper reality." That deeper reality is spacetime. From the perspective of spacetime, time is not something fundamentally different from space. They are different aspects of a four-dimensional geometry. An event in spacetime is specified by 4 coordinates, 3 spatial coordinates, and 1 temporal coordinate. The distance between 2 events in spacetime is determined by the Minkowski metric, a mathematical formula that combines spatial and temporal separation in a specific way. This Minkowski metric has a peculiar property. Unlike Euclidean space where distances are always positive, the spacetime metric can be 0 even when the spatial distance is not 0. Specifically, the spacetime interval along a light ray is always 0. This reflects the fact that light travels at the same speed for all observers. Light traces a particular kind of path through spacetime, and this path has 0 spacetime interval. The visualization of spacetime is difficult because we live in 3 spatial dimensions plus time, and we are used to thinking of time as different from space. But mathematically, once you embed spacetime as a 4-dimensional manifold, you can apply geometric techniques to understand it. A moving object traces out a path through spacetime called a world line. A stationary object traces a vertical world line straight up in the time direction. A fast-moving object traces a world line tilted more toward the horizontal, the spatial directions. The faster something moves through space, the more its world line tilts toward the space directions. Light traces a world line at a 45-degree angle in appropriate units, where the speed of light is 1. The insight that space-time is a geometric object, not just a stage where events happen, proved to be extraordinarily fruitful. It suggested that if gravity could be understood as the geometry of space-time, as a curvature of space-time, rather than as a force in the Newtonian sense, then gravity could be described within the same geometric framework. This suggestion would lead Einstein to general relativity, which is not just a theory of motion and time, but a theory of the very structure of space-time itself. But even within special relativity, the geometric view of space-time revealed something profound. Time and space are not separate. They are two aspects of a single four-dimensional reality. You cannot change your velocity without changing your orientation in space-time. And this changes which direction you consider the time direction. Different observers, moving at different velocities, literally have different senses of which direction is the future. They have different times. And all of these different times are equally valid. There is no universal future. There is no universal past. There are only the world lines of objects, tracing paths through space-time and the local sense of time that each observer carries with them. Gravity bends time. In 1907, a few years after publishing Special Relativity, Einstein had what he would later call the happiest thought of his life. He imagined a man falling freely from the roof of a house. For this man, Einstein realized, the gravitational field does not exist. In the man's reference frame, he is not being pulled downward by gravity. He is simply moving inertially, undisturbed by any force. This thought revealed something profound. Gravity is not a force like other forces. Gravity is not something that acts on objects from a distance. Gravity is something to do with the geometry of space-time itself. If you are standing on Earth's surface, you feel a force pulling you down. But in the deeper sense, the Earth is accelerating upward toward you. You are at rest relative to the ground, and the ground is pushing you upward, accelerating you. You feel the force of this acceleration. If you were in free fall, you would feel no force. You would be moving inertially through space-time. Einstein spent 8 years developing this insight into a complete theory. The result was the General Theory of Relativity, published in 1915. General Relativity reconceives gravity entirely. Gravity is not a force acting between bodies. Gravity is the curvature of space-time itself. Massive objects, the Earth, the Sun, stars, curve the space-time around them. This curvature affects how objects move through space-time. An object moving through curved space-time follows a geodesic, the straightest possible path given the curvature. From a distance, it looks like the object is being pulled by a force toward the massive body. But up close, in the object's own reference frame, it is simply moving straight. The curvature makes straight motion appear as if there is a force. Einstein expressed this beautifully. Matter tells space-time how to curve, and space-time tells matter how to move. Space-time is not an inert stage where physics happens. Space-time is dynamical. It responds to the presence of matter and energy. And in curvature, time itself is affected. Near a massive object, space-time is curved more steeply. This means that time runs differently near the massive object than it does far away. Time runs slower near a massive object. The stronger the gravity, the slower time runs. This can be derived from the mathematics of general relativity, but it is also intuitive once you think about it geometrically. Near a massive object, space-time is warped. The time direction is tilted and stretched. Time passes more slowly. Far from the massive object, space-time is flatter, and time passes more quickly. This effect is called gravitational time dilation. It is different from the velocity-based time dilation of special relativity, but related. Just as moving clocks run slow compared to stationary clocks, clocks in strong gravitational fields run slow compared to clocks in weak gravitational fields. This has real, measurable consequences. Atomic clocks placed at different altitudes run at different rates. A clock at the top of a mountain runs faster than an identical clock at sea level because it is farther from Earth's gravitational field. The difference is tiny, about 30 billionths of a second per day per kilometer of elevation, but it is measurable and real. GPS satellites orbiting Earth at altitude experience gravitational time dilation. Their clocks run faster than clocks on the ground because they are farther from Earth's gravity. Without accounting for both velocity-based time dilation, satellites move fast, and gravitational time dilation. Satellites are high, GPS would be inaccurate. The two effects work in opposite directions and partially cancel, but not completely. The technology that guides us to precise locations on Earth requires an understanding of how gravity affects time. Where time stops. The most extreme consequence of general relativity is the black hole. A black hole is a region of space-time that is so curved, so warped, that the curvature approaches infinity. At the center of a black hole is a singularity, a point where space-time curvature becomes infinite, and the usual laws of physics break down. Surrounding this singularity is the event horizon, the boundary beyond which nothing can escape, not even light. Light traveling outward from inside the event horizon falls back down into the black hole. The event horizon is the point of no return. What does this have to do with time? Everything. At the event horizon of a black hole, time effectively stops. From the perspective of a distant observer, watching an object fall toward the event horizon, the object's clock appears to run slower and slower as it approaches the horizon. The time intervals between ticks of the clock grow longer. The object appears to approach the horizon asymptotically, slower and slower, never quite reaching it. From the perspective of the object itself, falling toward the horizon, something different happens. The object experiences tidal forces. The difference in gravitational pull between its head and feet becomes stronger and stronger. But if the black hole is large enough, the tidal forces might be relatively gentle at the event horizon. The object would cross the event horizon in finite proper time. From the perspective of the object, it would cross the horizon, pass the singularity, and experience spaghettification, being stretched and torn by tidal forces. But this would happen quickly, in finite time from the object's perspective. But from the perspective of a distant observer, the object never actually crosses the horizon. It appears frozen at the horizon. Its clock stopped, its image red-shifted into invisibility. Time and gravity are so deeply connected that at the horizon of a black hole, time itself seems to come to a stop. This is not a metaphor. The geometry of space-time is such that the time direction becomes space-like at the event horizon. The future and the singularity are in the spatial directions. There is no future beyond the event horizon in the way we usually think about future. Once you cross the event horizon, the forward light cone, the region of space-time you can causally affect, points inward. The only future available to you is toward the singularity. In this sense, you might say that time stops being time at the event horizon. It becomes space. You cannot avoid the singularity any more than you can avoid moving forward in time outside the black hole. The singularity is not in your future in the time direction. The singularity is in your future in the spatial direction. You will reach it, just as you will reach tomorrow. Black holes transform our understanding of time in the most radical way. They show that time is not a universal thing that flows everywhere. Time is woven into the structure of space-time, and near massive objects, near the sites of intense gravity, time becomes something alien and strange. And in the heart of a black hole, time as we understand it ceases to exist. Time gravitates. Einstein's general relativity revealed something that seems almost impossible at first. Time gravitates. By this we mean that the energy carried by time, the way time's passage affects the space-time geometry, has gravitational effects. In the equations of general relativity, what sources the curvature of space-time is not just mass, but the entire energy-momentum tensor, which includes all forms of energy and momentum, including the gravitational field itself. This leads to a feedback effect. Gravity curves space-time. The curvature of spacetime affects how clocks run. Clocks running at different rates constitute different flows of time. These different flows of time have gravitational effects, so time itself contributes to gravity. This is a subtle effect, but it has been confirmed experimentally. The very precise measurements required by GPS and other technologies have verified that time dilation due to gravity is real and measurable. A more dramatic manifestation is gravitational waves. When massive objects accelerate, two black holes orbiting each other, for example, they create ripples in space-time itself. These ripples propagate outward at the speed of light. They are waves in the fabric of space-time, affecting both the spatial geometry and the temporal geometry as they pass. Gravitational waves were predicted by Einstein in 1916, but were not directly observed until 2015, when the LIGO experiment detected them. The detection was revolutionary. It confirmed Einstein's predictions made a century earlier. It opened a new window on the universe, and it demonstrated that space-time itself is real and dynamical. Space-time is not just an abstract mathematical construction. It is something that can wave, ripple, propagate. It is real. And time, being part of space-time, is real in a way that goes beyond human experience. When we stand on Earth's surface, we feel the force of gravity. This force is, in Einstein's understanding, the effect of curved space-time on our motion. We are moving inertially through warped space-time. The warping causes our paths to curve toward the Earth. We experience this as being pulled downward, and the warping of space-time includes the warping of time. Time runs slightly slower at Earth's surface than it does at high altitude. This difference is tiny, but it is real. Every moment of your life, your clock runs a little slower than it would if you were in space, far from Earth's gravity. The difference is infinitesimal, but it is there. And this difference arises from the curvature of space-time caused by Earth's mass. Einstein showed us that time is not separate from space. Time is not separate from gravity. Time is not separate from the very structure of reality. Time is woven into the fabric of space-time. It responds to mass and energy. It affects gravity. It is affected by gravity. Time and gravity are two aspects of the same thing, the geometry of space-time itself. In this realization lies one of the greatest insights of human thought. We have learned that the universe is built not from things, but from space-time. And we are not observers of space-time from outside it. We are woven into space-time. Our lives are world lines through space-time. Our clocks measure proper time along our world lines. And in every moment, we are experiencing the geometry of the universe itself. The atomic world defies intuition. At the beginning of the 20th century, as Einstein was revolutionizing our understanding of space and time, another revolution was quietly beginning. Physicists studying the behavior of atoms and light at very small scales were discovering something profoundly strange. The rules that governed large objects, the rules of Newton and Maxwell and even Einstein, did not seem to apply to atoms and electrons and photons. The atomic world operated according to different principles. These principles came to be known as quantum mechanics. The first hint of strangeness came from the study of light. Light, which Einstein had shown to have particle properties in his explanation of the photoelectric effect, also clearly had wave properties. Waves of light diffract around obstacles. They interfere with each other, creating patterns of light and dark. But particles do not behave this way. If you shoot particles at a screen with two slits, they go through one slit or the other. You get two bright spots behind the slits, but if you shine light at two slits, you get an interference pattern, bands of bright and dark regions. This is because the waves going through the two slits interfere with each other. So is light a wave or a particle? The answer, which emerged gradually through the 1920s, is that light is both, and neither. Light is something that has both wave and particle properties depending on how you observe it. If you set up an experiment to detect the particle properties of light, you detect particles. If you set up an experiment to detect the wave properties, you detect waves. This is not a limitation of the experiment or the observer. This is a fundamental feature of nature. Light, and indeed all matter, has what is called wave-particle duality. But there is something even stranger. If you set up the two-slit experiment carefully and try to determine which slit the light goes through, something remarkable happens. The interference pattern disappears. The light goes through one slit or the other, and you get two spots instead of an interference pattern. The act of observing which slit the light goes through changes the behavior of the light. It changes the light from acting like a wave to acting like a particle. This is the double-slit experiment, perhaps the most famous experiment in quantum mechanics, and it reveals something deeply puzzling about the nature of observation and reality. Before you look, the light seems to exist in a state where it goes through both slits. After you look, it goes through one slit or the other. The act of observation seems to determine reality. Niels Bohr, one of the founders of quantum mechanics, emphasized the role of the observer. He argued that quantum phenomena cannot be described independently of the experimental arrangement used to observe them. The observer and the observed are not separate. The choice of what to measure affects what exists to be measured. This created deep philosophical puzzles. Does reality only exist when observed? Is consciousness somehow fundamental to the universe? Or is there something else going on? Something more subtle about the nature of measurement and existence? These questions have troubled physicists for a century. But the mathematics of quantum mechanics is clear and unambiguous. The double-slit experiment has been performed countless times, with electrons, with atoms, even with large molecules. The result is always the same. Observation changes the behavior of matter. Reality at the quantum level is profoundly different from reality at the human scale. Superposition and probability. To describe quantum systems, physicists use something called a wave function. The wave function is a mathematical object that contains all the information about a quantum system. It determines the probabilities of different outcomes when you make a measurement. But here is the strange part. The wave function describes the system as existing in a superposition of multiple states simultaneously. An electron does not have a definite position. Instead, it has a wave function that describes a probability distribution of positions. The electron exists in a smeared-out state, spread out over a region of space. Only when you measure the electron's position does the wave function collapse. The probability distribution becomes a definite value. The electron is found at a specific location. Before measurement, the electron did not have a definite position. The measurement creates the position. This interpretation of quantum mechanics is called the Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg. In the Copenhagen interpretation, the wave function is not a description of reality. It is a description of our knowledge about reality. Before measurement, we do not know where the electron is. Our knowledge is represented by the probability distribution. When we measure, our knowledge becomes definite. The wave function collapses from a superposition to a specific value. But there is something profoundly strange about this. The collapse is instantaneous. A wave function that describes an electron spread out over a region of space collapses to a definite position instantaneously. And if the electron is entangled with another electron far away, the measurement of one electron seems to affect the state of the other electron instantly. This appears to violate special relativity, which says nothing can travel faster than light. How can information about a measurement of one electron instantly affect another electron across the universe? This is called the EPR paradox, named after Einstein, Podolsky, and Rosen, who first described it. Einstein found this deeply troubling. He believed that quantum mechanics was incomplete, that there were hidden variables that determined the outcomes of measurements, and that once you knew these hidden variables, the universe would be deterministic again. But subsequent experiments, particularly those based on Bell's theorem, showed that hidden variables of the kind Einstein envisioned were impossible. The quantum world really does operate probabilistically. Measurement really does affect the system in a way that cannot be explained by hidden information that was already present. The act of observation is fundamental. Time plays an odd role in quantum mechanics. The Schrödinger equation, which governs how wave functions evolve, is deterministic. Given an initial wave function, the Schrödinger equation determines exactly how the wave function will evolve over time. The wave function spreads and changes in a predictable, lawful way. But this evolution happens in an abstract space of possibilities. The actual outcome of a measurement is probabilistic. Before measurement, the system is in a superposition. After measurement, it is in a definite state. The equation of motion is deterministic. The outcomes are probabilistic. This is a strange kind of time. It is not the time of Newton, which is deterministic. It is not quite the time of classical probability either, because the probabilities are determined by a wave function that obeys a deterministic equation. It is something new. Time in quantum mechanics is a framework in which possibilities evolve deterministically, but actualities are probabilistic. The future is determined probabilistically from the present, but the present moment is not determined from the past. Measurement creates actuality from possibility. And what counts as a measurement, what causes the wave function to collapse, remains philosophically mysterious. Entanglement and non-locality. Two particles can become entangled. When they are, measuring a property of one particle instantly affects the state of the other particle, no matter how far apart they are. This is one of the most profound discoveries of quantum mechanics. Imagine two photons created together and then separated. You give one to Alice and send one to Bob. The photons are entangled. Alice and Bob are far apart. Alice measures the polarization of her photon and finds it is vertical. Instantly, Bob's photon becomes horizontally polarized. This happens even if Alice and Bob are separated by light years. The measurement by Alice instantly affects the state of Bob's photon. This seemed to violate causality. How can something that happens at Alice's location instantly affect something at Bob's location? Special relativity says that the speed of light is the ultimate speed limit for causality. Nothing can travel faster than light. How can the correlation between Alice and Bob's measurements propagate faster than light? The answer involves a subtlety. No information can be transmitted faster than light. The correlation between the measurements is faster than light, but it cannot be used to send a signal. Alice cannot control what result she gets when she measures her photon. The result is random. Only when Alice and Bob compare their measurements, by conventional communication that travels at light speed, do they discover that their measurements are correlated. So no signal is sent faster than light. But the correlation itself is instantaneous. This is what bothered Einstein. He called it spooky action at a distance. He believed that quantum mechanics was incomplete, that there must be some hidden variables that determine the outcomes before the measurements, such that the measurements are not actually affecting each other instantly. But in the 1960s, John Bell developed a theorem that showed such hidden variables were impossible if quantum mechanics predictions were correct. Subsequent experiments confirmed quantum mechanics predictions. Entanglement is real. Measurement of one particle instantly affects entangled particles. The universe is fundamentally non-local. Distant events can be correlated instantaneously. This does not make classical causality, where causes precede effects, impossible. Rather, it suggests that causality might be more subtle than we thought. Events can be correlated without one causing the other. The correlation is fundamental, and the instantaneity of this correlation suggests something strange about the nature of time at the quantum level. Time, as a parameter in which cause and effect unfold sequentially, seems to break down at the quantum level for entangled particles. The particles exist in a non-local, atemporal quantum state. Only when measured do they become localized in space and time. The spooky action at a distance suggests that time might not be the fundamental variable in quantum mechanics that it is in classical mechanics. Time might be emergent, arising from the entanglement structure of the universe. Two entangled particles do not experience time passing between them in the way we normally think about time. They are in a single quantum state, entangled across space. Measurement breaks this state into a past event and a future event. But before measurement, past and future might not be well defined for entangled particles. This is still speculative and not fully understood, but it hints that quantum mechanics might reveal something profound about the nature of time itself. The arrow of time. One of the deepest puzzles of quantum mechanics is the arrow of time problem. The Schrödinger equation, which governs the evolution of quantum systems, is reversible in time. If you reverse the direction of time and reverse the velocities of all particles, the equation still holds. The laws of quantum mechanics do not distinguish between past and future. They are time symmetric, and yet we live in a universe with a clear direction of time. The past is different from the future. Entropy increases. The sun shines and heats the earth. Eventually, the heat spreads out, and the sun cools down. We never see the reverse, a cool sun drawing heat from a cold universe and becoming hot again. This asymmetry between past and future is called the arrow of time. In classical thermodynamics, the arrow comes from the second law. Entropy increases. But where does entropy increase come from at the quantum level, where the laws are time symmetric? The answer is that entropy increase emerges from the initial conditions of the universe, combined with quantum mechanics. The universe began in a state of low entropy. This is a boundary condition. There is no dynamical law that requires the universe to start with low entropy. The fact that it did is a condition imposed at the Big Bang. Given that initial condition, and given the time-symmetric laws of quantum mechanics, entropy increases as time goes forward. This is because there are far more quantum states consistent with high entropy than with low entropy. As the universe evolves, it naturally explores more and more of these high entropy states. The arrow of time, then, is not built into the fundamental laws. It is a consequence of the initial conditions. The universe started in a very special, very low entropy state. As time progresses, it explores more typical, higher entropy states. From our perspective, living in a universe far from equilibrium, this creates the sense of time flowing forward, of the future being open and uncertain, of the past being fixed and known. But fundamentally, the universe is not asymmetric in time. The asymmetry is a consequence of where we are in the universe's evolution, near the low entropy initial state. In the infinitely distant future, when the universe reaches maximum entropy, the concept of time might become meaningless. In the infinitely distant past, before the Big Bang, time as we understand it might not have existed. We are living in a special era of the universe, where time is meaningful and directional. This is perhaps related to why life and consciousness exist. Conscious observers like us require organized structures, which require low entropy. We can only exist in eras of the universe that are far from thermodynamic equilibrium. And in such eras, time naturally has direction. We are, in a sense, prisoners of the arrow of time because we are made of low entropy matter. We are manifestations of the universe's initial condition. Our perception of time flowing forward is a consequence of our nature as organized structures in a universe that began in a state of extremely low entropy. The deepest questions remain. A century after quantum mechanics was developed, we still do not fully understand what it means. This is not a failure of physics. It is a reflection of how deep and strange quantum phenomena are. The mathematics is clear. The predictions are accurate. Quantum mechanics has been verified to extraordinary precision. But the interpretation, what quantum mechanics is actually saying about reality, remains deeply puzzling. When a wave function collapses upon measurement, what is collapsing? The wave function is a mathematical object in an abstract space. How does measurement in the physical world cause collapse in abstract mathematical space? Does consciousness play a role, as some interpretations suggest? Or is there a physical process of decoherence that causes the apparent collapse? Decoherence is the idea that when a quantum system interacts with its environment, the quantum coherence is lost, and the system appears to collapse into a definite state. But decoherence is not the same as collapse. The wave function still exists. The environment becomes entangled with the system. Decoherence explains why we do not observe superpositions of large objects. A macroscopic object constantly interacts with its environment, and this causes decoherence so rapidly that superpositions are impossible to maintain. But the fundamental question remains: does the wave function represent reality, or merely our knowledge about reality? Is there a reality independent of observation, or does observation create reality? These are not questions that physics can answer by itself. They are questions about the interpretation of physical theories, about the nature of reality and knowledge. Different physicists have different views. The Copenhagen interpretation, which treats the wave function as knowledge and measurement as creating reality, remains popular. The many worlds interpretation, proposed by Hugh Everett, suggests that the wave function is the whole of reality, and that measurement causes the universe to branch into multiple branches, each with a different outcome. In this interpretation, there is no collapse. All possible outcomes happen. You measure the electron's position, and in one branch of the universe you find it here, and in another branch you find it there. Both are real. Objective collapse theories propose that the wave function really does collapse physically, governed by stochastic laws that we have not yet discovered. Pilot wave theory, proposed by de Broglie and developed by Bohm, suggests that particles are guided by a quantum field, and that this provides a deterministic picture while reproducing all of quantum mechanics' predictions. These interpretations have different implications for the nature of time. In the many worlds interpretation, all times are equally real. All branches exist. There is no becoming, only the static geometry of the multiverse. In objective collapse theories, collapse is a real physical process, and time is the dimension along which this process unfolds. In pilot wave theory, particles follow deterministic trajectories, suggesting a more classical notion of time. The relationship between quantum mechanics and relativity is also puzzling. Quantum mechanics operates in a space-time that is fixed and predetermined. Relativity says that space-time is dynamical, curved by matter and energy. Merging these two theories into a quantum theory of gravity is one of the great unsolved problems of physics. In such a theory, space-time itself would be quantum. Space-time would not be deterministic. Time would not be a smooth parameter, but something quantized, perhaps made of discrete units at the Planck scale. The nature of time at the smallest scales, near the singularity of black holes or the Big Bang, remains unknown. We do not have a theory that can describe it. And yet, tangled up in these deepest mysteries of quantum mechanics and quantum gravity is something that might revolutionize our understanding of time. Some physicists speculate that time might be emergent, arising from entanglement patterns in a more fundamental, timeless quantum theory. Others suggest that time might be an artifact of the quantum decoherence process, that time emerges when a quantum system becomes entangled with its environment. If time is emergent rather than fundamental, then time is not part of the bedrock of reality. Time is something that arises under certain conditions, something that appears in our universe but might not appear in other regimes. This is a radical idea. It suggests that asking what is time might be like asking what is the color of truth. It might be a category error. Time might not be a thing at all. It might be a way that the universe describes itself when viewed from a particular perspective. The deepest mysteries of quantum mechanics point toward a revolution in our understanding of time that is still unfolding. The specious present. There is a fundamental mismatch between physics and psychology. Physics describes time as a dimension, like space. Past, present, and future are all equally real. Events are arranged along the time axis like points in space are arranged along a spatial axis. But this is not how we experience time. We experience time as flowing. We experience a distinct present moment separating a fixed past from an open future. Right now, as you listen to these words, there is a sense of the present moment. The sound you are hearing is happening now. The words I spoke moments ago are in the past. The words I have not yet spoken are in the future. This distinction between past, present, and future feels fundamental to human consciousness. But if you ask a physicist whether the present moment has any physical reality, the answer is complicated. In relativity, the present is not absolute. Different observers moving at different velocities will disagree about which events are happening now. There is no universal present moment. There is only the local sense of now that each observer carries with them. And yet, subjectively, the sense of present is overwhelming. This puzzle has occupied philosophers and psychologists for centuries. The term specious present was coined by William James, the American psychologist and philosopher, in the late 19th century. James observed that we do not experience isolated instants. We do not experience time as a sequence of disconnected moments. Rather, we experience duration. When you listen to a piece of music, you experience the notes as forming a melody. You hear the current note, but you also hold in mind the notes that just happened, and you anticipate the notes that are about to come. The present moment is not a knife-edge instant. It is a window of duration, typically about 3 seconds. This 3-second window is the specious present, the experienced present moment. Neurologically, this window seems to be created by the way the brain integrates sensory information. The brain does not process signals instantaneously. Sensory signals travel through neural pathways, taking time to reach the cortex where they are processed. Different sensory modalities, vision, hearing, touch, have different latencies. The brain must somehow synchronize these signals into a unified experience of the present. The result is that the now that you experience is not the moment when events are happening. It is a moment about a quarter second to a half second in the past. When you see something happen, there is a delay while the visual signal travels from your eye, through the optic nerve, to the visual cortex. When you hear something, there is a delay while the sound travels through the air to your ear, then through the auditory system to the cortex. The brain compensates for these delays. When you watch a person speaking, your brain synchronizes the visual image of the lips with the sound of the voice. even though the sound reaches your brain much slower than the visual signal. The brain is a time-binding machine, integrating signals from different times into a unified sense of the present. And this present extends not just into the immediate past, but into the immediate future. The brain constantly anticipates what is about to happen. Your visual system predicts where a moving object will be. Your auditory system predicts the next note in a melody. Your motor system predicts the sensory consequences of your actions. The present moment includes this anticipatory component. You are constantly living slightly in the future, preparing for what is about to happen. The specious present, then, is not a moment of time. It is a duration in which the brain integrates past sensations, present stimuli, and future predictions into a unified conscious experience. Outside this window, events are either forgotten or anticipated, but not directly experienced. Within this window, everything feels like it is happening now. The physicist's description of time as a dimension on which all moments exist equally is mathematically elegant, but psychologically alien. The psychologist's description of time as flowing, with a moving present moment, is intuitively compelling but physically strange. These two descriptions are difficult to reconcile, but they may both be true from their different perspectives. Physics describes the structure of space-time. Consciousness describes the structure of experience. And experience of time, as William James understood, is not a simple given. It is constructed by the brain. It is a story that the nervous system tells itself about what is happening. Memory as time binding. Without memory, there would be no sense of time's passage. Without memory, the present moment would exist in complete isolation. The past would not exist. There would be no before, no sequence of events, no narrative. Yet memory is not a recording. Memory is a construction. When you remember something, you are not accessing a perfect recording of the past. You are reconstructing it, filling in details, organizing it according to current concerns and emotional states. Each time you remember something, the memory changes slightly. And this has profound implications for how we experience time. The psychologist Daniel Schacter has identified what he calls the 7 sins of memory. These are not failures of the memory system. They are consequences of the way the brain has evolved to handle information. One of the key sins is misattribution. You can remember an event accurately, but misattribute it to the wrong time or place. You remember a conversation, but forget when it happened. Another is absent-mindedness. You intended to do something, but forgot to do it. Another is transience. Recently formed memories fade away naturally. These are not bugs in the memory system. They are features. The memory system is optimized for extracting the gist of experience, the essential meaning, rather than preserving detail. This is adaptive for survival. What matters is not the exact details of what happened, but the patterns and lessons that can be extracted from experience. If you remember that a particular plant is poisonous, it does not matter if you remember the exact color of the berries or the exact location where you encountered it. What matters is that you can recognize the plant and avoid it in the future. Memory is reconstructive and adaptive, not reproductive and literal. And because memory is constructed in the present, the past is continuously being revised. The story you tell about your life changes as you change. An event that seemed tragic 10 years ago might now seem like a necessary lesson. An event that seemed wonderful might now seem to have harbored hidden pain. Your past is not fixed. It is fluid, reconstructed, and reinterpreted in light of new experiences and new understanding. The philosopher David Hume made a startling observation. He said that when he looked introspectively, he could not find a self. He found only a succession of impressions and ideas. He found thoughts and sensations arising and passing away. But he did not find a unified self that persists through time. This is one of the deepest insights in philosophy. The sense of a continuous self that persists from the past into the future is something constructed by memory and narrative. You are a different person now than you were 10 years ago. Your cells have been replaced. Your beliefs have changed. Your desires have changed. Yet you feel like the same person because you have memories that connect your past self to your present self. And you have a narrative, a story that you tell about yourself. This narrative weaves together disparate experiences into a coherent whole. It gives your life meaning and direction. It creates the sense of a self persisting through time. But it is a construction. The narrative self is not a given. It is created by the brain as a useful way of organizing experience and predicting the future. And this narrative self is what experiences time as flowing. A being with no memory and no narrative sense of self would not experience time as flowing. It would exist in an eternal present, experiencing each moment in isolation. The fact that we experience time as flowing, as forming a narrative from past to future, is because we are creatures whose consciousness is organized around memory and narrative. We are time-binding creatures. We bind together moments through memory into a coherent story. And in doing so, we create the experience of a flowing present, a moving now that carries a continuous self from a real past into an open future. Anticipation and the future. Just as the past is reconstructed from memory, the future is constructed from anticipation. The brain is constantly predicting what will happen next. This is not abstract prediction. This is a fundamental feature of how the brain operates. Every sensory system in the brain is predictive. The visual cortex does not merely process the current visual input. It uses that input to predict what will be seen in the next moment. The auditory cortex does not merely process the current sound. It uses that sound to predict the next note, the next word, the next sound. The motor cortex does not merely execute an action. It predicts the sensory consequences of that action. This predictive aspect of perception is revealed by optical illusions and perceptual phenomena that would be puzzling if perception were purely reactive. When you watch a moving object, you perceive the position slightly ahead of where the object actually is. Your brain is extrapolating the trajectory. When you listen to a familiar song with a sudden pause in the middle, you still hear the ghost of the note that should have been there. Your brain predicted it, and the prediction is part of your conscious experience. The brain is not a passive receiver of information. It is an active predictor. And because the brain is constantly predicting, the future is constantly present in consciousness. You are never living purely in the present moment, reacting to what is actually happening. You are living slightly in the future, anticipating what is about to happen. Your experience of the present is shaped by your expectations of the future. This is why surprise is so salient. When something happens that violates your prediction, your attention snaps to it. You become acutely aware of the present moment when reality does not match your expectations. This predictive nature of consciousness has profound implications. It suggests that the experience of the future as open and undetermined is itself a prediction. Your brain predicts multiple possible futures. You experience the space of possibilities. And then, as time unfolds, one of those possibilities becomes actual. But before that moment, you do not know which one will happen. The openness of the future is real, at least from the perspective of consciousness. Your brain cannot perfectly predict what will happen. The future remains open. This is true even if, as physics suggests, the future is determined by the laws of physics and the current state of the universe. From the perspective of consciousness, lacking complete information, the future is open. This distinction between physical determinism and conscious indeterminacy is important. It means that even if the universe is deterministic at the physical level, from the perspective of a conscious being lacking complete information, the future is genuinely uncertain. And this uncertainty is what creates the experience of choice. When you make a decision, you experience it as a choice among open possibilities. Physics might say that your decision was determined, that given your brain state and the laws of physics, only one choice was possible. But consciousness does not have access to this information. Consciousness experiences an open space of possibilities, any of which might happen. And consciousness experiences itself as choosing among these possibilities. The experience of agency, the sense that you are choosing your actions and your future, arises from the inability of the conscious mind to predict perfectly. It arises from the genuine openness of the future, from the perspective of consciousness. Anticipation is not just about expecting the future. Anticipation is about creating the future through action in the present. When you reach out your hand to pick up a cup, you have already predicted where your hand needs to be when it reaches the cup. The prediction shapes the action. The action shapes the future. And through this process, anticipation becomes a form of creating time itself. Altered states and the elasticity of time. The experience of time is not fixed. It is malleable. It can be stretched, compressed, altered. In different states of consciousness, time feels different. Anyone who has meditated knows this. When the mind is still, when thought ceases, when you are simply observing the flow of breath and sensation without commentary, time seems to slow down. A meditation session that lasts 20 minutes can feel much longer, filled with a vast span of present moment experience. This is not an illusion. It reflects a real change in how consciousness is operating. The brain is no longer constructing a narrative, no longer organizing experience into a story. It is simply observing. And in observation without narrative, the ordinary markers of time, the progression of thoughts, the sense of anticipation and planning, are absent. Time becomes more spacious. Conversely, when you are deeply engaged in an activity that you love, when you are in what the psychologist Mihaly Csikszentmihalyi calls a flow state, time seems to pass very quickly. Hours can feel like minutes. You emerge from the activity surprised at how much time has passed. In a flow state, the self is minimized. You are not observing yourself. You are not thinking about what you are doing. You are simply acting in perfect attunement with the task. And in the absence of self-awareness, in the absence of a narrative self-monitoring and planning, time disappears. The experience is timeless. Dreams are another arena where time operates strangely. In dreams, time is not linear. You can experience multiple events in a sequence that seems to span hours, but the whole dream lasts only a few minutes. Or you can spend what feels like a few seconds in a dream and wake to find that hours have passed. In dreams, causality is different. Effects precede causes. Spatial logic is different. You can be in two places simultaneously. The narrative logic that structures our waking experience of time is absent. And so time, which seems so fundamental to waking consciousness, becomes fluid and negotiable. Under the influence of psychoactive drugs, time perception is dramatically altered. Hallucinogens like LSD or psilocybin can make minutes feel like hours. Time seems to dilate, or conversely, time can seem to contract and disappear. Some people report experiencing something outside of time altogether, a timeless state of being where the distinction between past, present, and future dissolves. These altered states show us something important. Time is not a given feature of consciousness. Time is something that consciousness constructs. Change the brain state, and you change the experience of time. This suggests that the time we experience in ordinary waking consciousness is a particular construction of the brain, optimized for navigating the physical world and interacting with other people. But this is not the only way consciousness can organize temporal experience. Other organizations are possible, and these possibilities hint at something profound. The temporal structure of consciousness may be more contingent, less fundamental than we usually assume. Time, as we experience it, linear, flowing, with a present moving from past to future, may be a particular way that consciousness organizes experience. But it is not the only way. And this raises a question. If consciousness can experience time in radically different ways, what does this tell us about the nature of time itself? Evolution's gift. Why does consciousness experience time at all? Why did evolution create beings that experience duration, that anticipate the future, that remember the past, that have a sense of a moving present? The answer is that time perception is survival advantage. A creature that can only experience the immediate present cannot plan for the future or learn from the past. A creature that cannot anticipate dangers is vulnerable. A creature that cannot remember what happened before is condemned to repeat the same mistakes. The ability to mentally represent the past and future, to use memory and anticipation to navigate the world, is of immense survival value. And consciousness, the subjective sense of experiencing time, of being present in the moment, of having a perspective on the flow of events, may be inseparable from these practical abilities. Time perception evolved because the creatures that experienced time survived better than those that did not. They could anticipate predators and prey. They could remember which plants were safe to eat. They could plan complex actions across time. They could coordinate with other members of their group. Animals with sophisticated time perception, mammals, birds, some reptiles, are generally more intelligent, more flexible, more successful than animals without it. There is a relationship between temporal sophistication and behavioral sophistication. But there is something else that time perception enabled. There is something that goes beyond mere survival. Humans do not just use time perception to navigate the physical world. Humans use time perception to create meaning. Because we can remember the past and anticipate the future, we can construct narratives about ourselves. We can see our lives as stories with meanings and directions. We can reflect on where we came from and imagine where we are going. We can feel purpose and direction. We can feel that our lives matter. An ant does not construct a life narrative. An ant does not feel that its life has meaning beyond the immediate survival tasks. But humans do. We are creatures who experience ourselves as protagonists in an ongoing narrative. And this narrative sense of self, this sense that our life is a story being told across time, is uniquely human. Or, at least, it seems to be rarer in the animal kingdom. It is an evolutionary gift, or perhaps an evolutionary burden. It gives life meaning. It also creates suffering. We suffer because we can remember pain and regret the past. We suffer because we can anticipate loss and fear the future. We suffer because we are mortal, and we know that we are mortal. A being that lived only in the present moment would not suffer from memory or anticipation or mortality. But it would also not have the sense of self, the sense of meaning, the sense that its life matters. Humans have chosen, through evolutionary history, consciousness over timelessness. We have chosen the ability to experience meaning over the peace of a timeless present. This choice was not conscious, of course. It was driven by survival advantages. But the result is that we are creatures for whom time is the deepest dimension of reality. We are time-binding, narrative-constructing, meaning-making creatures. And, in the architecture of human consciousness, time is the thread that connects it all. Without time, there would be no consciousness as we know it. Without consciousness, there would be no experience of time. The two are woven together. And this weaving, this profound entanglement of time and consciousness, may be one of the most fundamental features of reality. It may be that time and consciousness are not separate phenomena that happen to interact. It may be that they are two aspects of the same thing. That consciousness is, in some deep sense, the experience of time. And time is, in some deep sense, the structure that makes consciousness possible. The Industrial Revolution stole time. There was a moment in human history when time changed meaning. It was not a moment marked by any particular event, but it was gradual and profound. It began with the industrialization of Europe and North America in the 18th and 19th centuries. Before this moment, time was primarily cyclical. The seasons turned, crops were planted and harvested. The sun rose and set, the moon waxed and waned. Human life was organized around these natural cycles. A peasant in medieval Europe did not live by clock time. They lived by sunrise and sunset. They worked in the fields when there was light, rested when there was darkness. In winter, when the days were short, there was less work and more rest. In summer, when the days were long, there was more work and less rest. Time was locally variable. A market town had its own rhythm. The blacksmith opened his shop when people needed tools. The baker baked when there were customers. There was no notion of opening at 9 a.m. There was no schedule. There was only the natural flow of the day and the seasons. Religious life was organized around bells marking the canonical hours: matins, lauds, prime, terce, sext, none, vespers, compline. But even these times were approximate. They were anchored to the position of the sun, which varied throughout the year. There was no universal time. Each monastery kept its own time. And this was fine. People did not need to coordinate precisely. They lived in small communities. The world was local. Then came the factory. The factory required something the countryside did not. The factory required synchronized labor. Hundreds of people had to arrive at the same moment. They had to work for the same duration. They had to stop at the same moment. And crucially, they had to repeat this every day, on the same schedule, with no variation for season or weather or individual need. The factory required clock time. Not just any clock time, but precise, synchronized, standardized clock time. A worker could not arrive at some time in the morning. They had to arrive at 6 a.m. If they were 5 minutes late, they lost wages or lost their job. The modern obsession with punctuality was born. Being on time became a moral virtue. Being late became not just inconvenient but a character flaw. E.P. Thompson, the historian, wrote extensively about this transformation. He showed how the shift from task-oriented time to clock-oriented time was experienced as oppressive by workers. Previously, work was measured by what was accomplished. You worked until the task was done. If it took 4 hours, you worked 4 hours. If it took 8, you worked 8. There was flexibility. The worker had some control over the rhythm of work. But with factory time, work was measured by duration. You worked for 8 hours, whether the task was finished or not. You worked by the clock. The clock became the master. Your body became subservient to the clock's demands. Your biological rhythms, your energy levels, your need for rest did not matter. The clock did not care. The clock was absolute. This transformation had psychological effects. Workers experienced alienation not just from the products of their labor, but from time itself. Time became something imposed from outside, something you endured rather than something you inhabited. The natural time of the body, the cyclical time of seasons, the task-oriented time of meaningful work. All of these were replaced by the abstract, uniform, relentless time of the clock. And as industries spread, as railroads connected towns, as telegraph wires transmitted information across distances, the need for standardized time became universal. The railway companies, as we discussed earlier, imposed time zones. Governments adopted them. By the early 20th century, the entire industrialized world operated on standardized, synchronized clock time. Time had become a commodity. You could buy an hour of labor. You could sell an hour of your time. Time had value. Time could be wasted or used well. The phrase "time is money" emerged during this period, and it reflected a real change in how time was understood. For a medieval peasant, time was not money. Time was simply the medium in which life happened. For an industrial worker, time was money. Your wage was paid by the hour. Your value was determined by how much time you could sell. This commodification of time was not inevitable. It was a choice, though not a conscious one. It emerged from the demands of industrial production. But once established, it became the water we all swim in. We cannot imagine time as anything else. We wake to alarms. We check our watches. We schedule our days. We worry about having enough time. We try to save time or find time. We are all industrial workers now, even if we do not work in factories. The ideology of clock time has colonized every aspect of life. Even our leisure time is scheduled. We book a restaurant reservation at 7:30 p.m. We schedule a doctor's appointment at 2:15 p.m. We meet friends at a specific time. We coordinate our lives through the medium of clock time. This is so normal to us that we cannot see it as a choice. But it is a choice, and it came with costs. We lost the cyclical rhythms of natural time. We lost the task-oriented sense of work. We gained efficiency, coordination, the ability to organize complex societies. But we also gained a sense of time pressure, of never having enough time, of time slipping away. We gained anxiety about the passage of time, about mortality, about our limited allotment of hours. The Industrial Revolution did not invent the clock. It gave the clock power over human life. Polychronic and monochronic cultures. Not all cultures experience time the same way. Anthropologists and cross-cultural psychologists have identified two different temporal orientations, polychronic and monochronic. Monochronic cultures are oriented toward clock time. Time is linear, segmented into precise units. One thing happens at a time. Events are scheduled in advance. Meetings start and end at specified times. Time is a scarce resource that must be managed carefully. This is the orientation of industrial, technologically advanced Western societies. It is the orientation of the United States, Northern Europe, Germany, Switzerland. It is the orientation that values punctuality, efficiency, planning. Polychronic cultures have a different relationship with time. Time is more flexible, more fluid. Multiple things can happen at once. Schedules are approximate. Relationships take precedence over clock time. If you are meeting a friend and a relative stops by, you will spend time with the relative, even if it makes you late for the friend. The relationship is more important than the schedule. This is the orientation of many cultures in Latin America, Africa, the Middle East, and parts of Asia. It is the orientation of societies that are more relationship-focused than task-focused. Neither orientation is better. They are adapted to different social contexts and different values. Monochronic time works well for coordinating large-scale, complex activities. It works well for bureaucracies and industries. It enables synchronized action across many people. But it comes at a cost. It can make life feel rushed. It can prioritize efficiency over meaning. It can create stress and time anxiety. Polychronic time works well for relationships and flexibility. It allows for spontaneity. It prioritizes people over schedules. But it can make large-scale coordination difficult. It can create inefficiencies. It can make the unexpected normal in ways that are not always convenient. The anthropologist Edward Hall, who developed this framework, noted that Americans tend to be highly monochronic, while Arabs, Latin Americans, and many Africans tend to be more polychronic. But within every culture, there is variation. And importantly, culture can change. As societies industrialize, they tend to adopt more monochronic time orientation. As traditional ways of life are replaced by modern systems, the experience of time shifts. This shift is not inevitable, but it is common. And it represents a kind of cultural loss. When a culture shifts from polychronic to monochronic time, something of value is lost. The sense of relationships mattering more than schedules, the flexibility to respond to the present moment, the lack of time anxiety, these are lost. They are replaced by efficiency, coordination, and the ability to plan into the distant future. But there is a growing recognition that the monochronic orientation has costs. The stress and time anxiety of industrial societies are real. The sense of being perpetually rushed, of never having enough time, of time slipping away, these are widespread experiences. And some people are seeking to reclaim a more polychronic, relationship-oriented, present-focused way of being. The slowness movement, mindfulness practices, sabbaticals, digital detoxes, these all represent attempts to escape from the tyranny of monochronic clock time. They represent an attempt to reclaim a different relationship with time, but they are swimming against a cultural current. The global adoption of industrial time structures through technology is nearly complete. Even in polychronic cultures, the clock is colonizing time. Digital devices enforce schedule keeping. Global commerce requires synchronized timekeeping. The world is becoming increasingly monochronic. But perhaps the very pressure of this trend is creating a backlash. Perhaps people are beginning to recognize that time is not just something to be managed efficiently. Perhaps time is something to be experienced, inhabited, enjoyed. Perhaps there are ways of being in time that are different from the industrial, commodified version that we have inherited. And perhaps exploring these different ways of being in time is not a luxury. Perhaps it is essential for human flourishing. Technology's acceleration. The experience of time accelerates with each new technology. Before writing, human memory was the only storage. Knowledge had to be maintained by oral tradition, by people remembering and retelling. This was efficient in some ways. The stories were adapted to the community's needs. But it was also limiting. You could only transmit what could be memorized and retold. Writing changed this. Knowledge could be stored external to the mind. Books preserved information across generations. Civilizations could accumulate knowledge. But writing also was slower than speech. To communicate across space, you had to physically transport a manuscript. Knowledge traveled at the speed of a messenger on horseback. The printing press accelerated this. With mass-produced books, knowledge could spread faster and to more people. But still, the speed was limited to the speed of physical transport. Then came electricity and the telegraph. For the first time, information could travel faster than a physical messenger. A message could be sent across a continent in minutes. This was revolutionary. Time and space were compressed. Distant events could be known about almost instantaneously. The speed of communication suddenly increased by orders of magnitude. The telephone further accelerated communication. You could speak across vast distances in real time. Radio and television allowed one-to-many communication. A speaker could address millions of people simultaneously. Time became synchronized on a global scale. A president could address the nation. A news event could be witnessed by millions of people at the same moment. Radio and television created a sense of global simultaneity. They made the present moment a shared experience for vast numbers of people. Then came computers and the internet. Information could travel at the speed of light. Digital devices made it possible to access almost any information almost instantly. The speed of communication reached its theoretical maximum, the speed of light through fiber optic cables, and the internet made it possible for any person to communicate with any other person on the planet. The world became connected in real time. This acceleration has had strange effects on the experience of time. On one hand, we have more time than ever before. Labor-saving devices have reduced the hours spent on work and housework. We have more leisure time, but we do not feel like we have more time. We feel rushed. We feel like we do not have enough time. Why? One reason is that the technologies that save time create new demands on our time. Email and messaging create an expectation of rapid response. Social media creates a need to be constantly updated. The internet creates an infinite supply of content to consume. We have more time available, but we have more to do with that time. Another reason is that the acceleration of technology has accelerated the rate of change in culture and society. In traditional societies, change was slow. A person could live their entire life in relative similarity to how their parents lived. But in modern society, change is rapid. Technologies emerge. Industries transform. Social norms shift. The future is unpredictable. This creates a sense of urgency. The present moment feels fragile and fleeting. You have to stay updated, stay ahead, stay relevant, or you will be left behind. The pace of life accelerates not just in terms of the speed of communication, but in terms of the rate of change. This creates a different kind of time anxiety than industrial societies experienced. Industrial societies created anxiety about being on time, about punctuality. Modern societies create anxiety about being left behind, about the future arriving too fast, about change happening faster than we can adapt. The pace of life has become dizzying for many people. And yet, many technologies promise to slow things down. Meditation apps, sleep tracking devices, wellness retreats, digital detoxes. There is a recognition that the acceleration is unsustainable, that something is being lost in the rush. But the technologies themselves seem to accelerate rather than decelerate. Each new innovation promises efficiency, speed, more time. But somehow, we end up with less. This is the paradox of technological acceleration. As technology speeds up communication and access to information, we feel more rushed, not less. As we gain access to more things, we feel we have less time to enjoy them. The promise of technology was that it would give us more leisure. But instead, it has colonized our leisure. The boundary between work time and leisure time has blurred. We check emails on vacation. We scroll social media in bed. Time has become fragmented. The rhythm of life has become erratic. We are always on, always connected, always available. There is a hunger for a different kind of time. A time that is not fragmented. A time that is not colonized by work. A time that is simply lived, experienced, inhabited without constant reference to productivity or efficiency. Finding such time in the modern world is increasingly difficult. But the very difficulty, the very hunger, suggests that something essential is missing. And that essential thing may be precisely the kind of time we have lost in the rush toward progress. The myth of productivity. Efficiency and productivity have become values in themselves. It is not enough to work. You must work productively. It is not enough to have leisure time. You must use leisure time productively. Productivity has become the measure of a life well lived. A productive person is someone who accomplishes things, who creates value, who makes progress. An unproductive person is someone who wastes time, who does nothing, who simply exists without adding to the world. This is a modern value. It is not universal. In many traditional societies, simply existing, being present, enjoying the company of others, is valued. There is no pressure to constantly be productive. But in industrial and post-industrial societies, productivity is king. We have internalized the values of capitalism. We see our time as a resource to be optimized. We try to combine activities. We multitask. We look for efficiencies. We feel guilty when we are not productive. If you spend an afternoon simply sitting, reading a book with no goal other than enjoyment, you might feel guilty. You are not being productive. You are not accomplishing anything. You are wasting time. But what if you are not wasting time? What if simply being, simply experiencing, is valuable in itself? What if a life that is not constantly producing is still a good life? The pressure for productivity creates stress. It creates the sense that there is never enough time. No matter how much you accomplish, there is always more to do. The to-do list never shrinks. There are always tasks undone, goals unmet, opportunities missed. This creates a chronic sense of failure, of not doing enough. And because productivity is measured in terms of measurable output, activities that are valuable but not measurable become invisible. Time spent with loved ones is valuable, but it is not productive. Time spent in reflection or contemplation is valuable, but it is not productive. Time spent in play, simply enjoying the present moment, is valuable, but it is not productive. And so, these things are squeezed out. They are luxuries to be indulged in when time permits. But time never really permits. There is always more that could be done. The myth of productivity says that a full life is a productive life. But perhaps that is wrong. Perhaps a full life is a life that includes all kinds of time, productive time and leisure time, time spent accomplishing and time spent simply being, time oriented toward the future and time present to the moment. The ancient philosophers recognized the value of leisure. The Greek word for leisure is skole, from which we get the word school. Leisure was not idleness. It was the time for philosophy, for reflection, for becoming educated. Leisure was the highest form of time, because it was time free from the demands of labor, available for the development of the mind and soul. The modern world has almost entirely lost this sense of leisure. We have conflated leisure with entertainment, with consumption. Leisure time is time to watch television, to scroll through social media, to consume products and experiences. It is not time for reflection, for philosophy, for becoming more fully human. We have lost the Greek understanding of leisure as the highest form of time, and we have lost something precious in doing so. There is a growing recognition that the pursuit of productivity is not delivering what was promised. We are more productive than ever before, at least in terms of economic output. But we are not happier. We are not more satisfied. We are not more free. We are more stressed, more anxious, more fragmented. Perhaps the problem is not that we are not productive enough. Perhaps the problem is that we have made productivity the measure of everything. Perhaps the time has come to reclaim a different relationship with time, one that values being as much as doing, presence as much as progress, slowness as much as speed. Imagining alternative futures. How we relate to time shapes the futures we imagine, and the futures we imagine shape the choices we make. Industrial culture imagined the future as progress. Technology would advance, society would improve, human life would become better, easier, more comfortable. This narrative of progress was incredibly powerful. It gave meaning to the present moment. The sacrifices we make now are for the sake of a better future. The long hours of factory work are endured for the sake of progress. The environmental damage caused by industrialization is acceptable because we are advancing toward a better world. But this narrative is beginning to crack. We have achieved the technological advances promised. And yet, life does not seem better in all the ways that matter. Anxiety is widespread. Depression is common. Loneliness is increasing even as we are more connected than ever. The future we were promised has arrived, and it is not what we expected. At the same time, we are facing new challenges that question whether progress can continue. Climate change threatens the future. The exponential growth that capitalism requires may be impossible on a finite planet. The technological systems we have built are creating new problems, even as they solve old ones. There is a growing recognition that the progress narrative may be a dead end. What alternatives are there? One alternative is the circular, cyclical vision of time that was common in traditional cultures. This vision sees time not as a linear progression toward a distant goal, but as cycles that repeat. The seasons turn. Life and death cycle. What goes down comes up again. There is a kind of stability and homeostasis in this vision. The future will resemble the past because time is cyclical. This vision is less driven by novelty and progress, but it can also seem fatalistic. If time is cyclical, why try to change things? Everything returns to where it was. Another alternative is what we might call a sustainability vision. In this vision, the future is not about endless growth and progress, but about finding a steady state where humans live within the limits of the planet. This vision is not cyclical in the traditional sense, but it is also not linear progress. It is a kind of equilibrium. The goal is not to constantly advance, but to maintain balance. This vision requires a different relationship with time. Instead of constantly looking forward to a better future, we would be more focused on preserving the present and the past. We would be more conservative in the sense of conserving what we have. This is not progress as it was traditionally understood, but it may be what we need. Yet another alternative is what we might call a catastrophe vision. In this vision, the future is not progress or equilibrium, but collapse. Industrial civilization will eventually fail. The technological systems that seem so robust will break down. The environment will become uninhabitable for humans. This is not a desired future, but many people see it as the likely future given current trends. This vision creates a kind of urgency to prepare, to create alternative ways of living that do not depend on the complex technological systems we have built. All of these visions, progress, cyclical, sustainable, catastrophic, shape how people relate to time and what choices they make. The future is not given. It is not predetermined. The future is created by the choices we make in the present, and the futures we imagine are constrained by the cultural narratives we have available, by the stories we tell ourselves about time and change. Perhaps the task of our moment is to expand the stories we tell. Perhaps we need new narratives about time and the future that are not trapped in the progress narrative, but also not entirely pessimistic. Perhaps we need stories that honor the past, are present to the moment, and imagine futures that are diverse, resilient, and humane. The time for new stories is now, because the time we inhabit and the futures we create depend on it. Does time really exist? This question sounds absurd. Of course, time exists. You experience it. You measure it. You can see it passing. But when philosophers and physicists ask whether time exists, they are asking something more subtle. They are asking whether time is a fundamental feature of reality, or whether it is something our minds impose on the world. They are asking whether the universe, at the deepest level, is temporal or atemporal. This question divides into several distinct positions, each with profound implications. The first position is eternalism. Eternalism says that all moments in time are equally real. The past, the present, and the future all exist in the same way. The past is not gone. It still exists, somewhere in the space-time continuum. The future is not yet to come. It already exists, somewhere in space-time. The present moment, which feels so special to us, is not objectively privileged. It is simply our location in time, like a location in space. This view is attractive to physicists because it is consistent with relativity. In relativity, space-time is a four-dimensional continuum. There is no preferred time direction, no privileged present moment. All moments exist on equal footing. The universe is a static four-dimensional block of space-time. We move through this block, and our experience of time passing is an illusion created by our limited perspective. We are beings that move through space-time at a particular trajectory, and we experience the unfolding of events along our trajectory as time passing. But the events are not actually unfolding. They already exist, eternally embedded in space-time. In eternalism, the future is not open. It is fixed. Your future actions are as real and as determined as your past actions. You will do what you will do. The only question is whether you know it now. This is deeply counterintuitive. We experience the future as open. We experience ourselves as making choices that affect the future. But if eternalism is correct, these experiences are illusions. The future is as fixed as the past. You are not really choosing. You are simply enacting a predetermined path through spacetime. The second position is the growing block universe. In this view, the past is fixed and real. The present moment is real. But the future does not exist yet. The universe is constantly growing, adding new moments to the block of spacetime. As time passes, the present moment advances, and new future moments become part of reality. This view preserves some of the specialness of the present moment. The present is where reality becomes determinate. The future is genuinely open and undetermined until it becomes present. This view is more consistent with how we experience time. The future feels open. We feel like we are making choices that affect what happens next. And in the growing block universe, this is true. The future really is open. Our choices really do matter. But the price of this view is that it conflicts with relativity. In relativity, there is no objective fact of the matter about which events are happening now for the universe as a whole. Different observers disagree about simultaneity. So if the present is constantly growing, adding new moments, which present? Whose present? The growing block view requires that there be an objective, universal present, but relativity seems to deny this. The third position is presentism. Presentism says that only the present moment exists. The past is gone. It no longer exists. The future has not yet come to be. It does not exist. Only the present moment is real. Everything that is real is now. This is the most intuitive view. It matches our experience. We live in the present. The past is over and done with. The future has not happened yet. But presentism has a problem. It seems to require an objective, universal present moment, and relativity denies that this exists. In relativity, events that are simultaneous in one reference frame are not simultaneous in another. So if only present events are real, and present is relative, then what is real? Different observers would disagree about what is real right now. This seems absurd, and yet, presentism remains appealing to many people because it matches our experience so well. Between these three positions, eternalism, growing block, and presentism, the physics community tends to favor eternalism. The mathematics of relativity seems to support it. But many philosophers and many ordinary people find eternalism deeply troubling. It seems to deny free will. It seems to make the present moment an illusion. It seems to imply that human agency is an illusion. The tension between what physics suggests and what human experience suggests may be one of the deepest puzzles in philosophy. It may be that physics is describing something true about the universe's structure, and human experience is describing something true about how consciousness interacts with that structure. The two might not be incompatible, but the reconciliation remains elusive. Perhaps time exists, but not in the way we usually think about it. Perhaps time is real, but the present moment is not. Perhaps the future is real, but not open. Perhaps we must learn to live with the strangeness and accept that time is not what it seems. The origin of time. If time is real, when did it begin? The Big Bang Theory says that the universe began about 13.8 billion years ago in an infinitely hot, infinitely dense state. Everything that exists emerged from this state. Space and time themselves emerged from it. But this raises a puzzle. If the universe began at the Big Bang, what came before? Was there time before the Big Bang? Did the Big Bang happen at a particular time? The answer, which emerged from Einstein's general relativity and has been refined by modern cosmology, is subtle. Time did not begin before the Big Bang. Rather, time itself emerged from the Big Bang. The Big Bang is not an event that happened in time. The Big Bang is the origin of time itself. To ask what came before the Big Bang is to ask a nonsensical question. Before implies earlier in time, but there is no time before the Big Bang. There is no before. The Big Bang is the beginning of the time dimension itself. The physicist Stephen Hawking developed an approach to this problem using imaginary time. In ordinary, real time, the universe expands from the Big Bang singularity. At the singularity, the equations of general relativity break down. Curvature becomes infinite. Physics ceases to apply. But if you rotate time into the imaginary direction, the singularity becomes smooth and regular. Imaginary time is geometrically equivalent to a spatial dimension. So near the origin of the real universe, the time dimension resembles a spatial dimension. The universe is finite but unbounded, like the surface of a sphere. Just as the surface of a sphere has no edge and no special starting point, the universe in imaginary time has no edge and no beginning. There is no moment of creation. There is no moment of creation. There is no before. The universe simply is, without origin or edge. This is a profound insight. It suggests that at the deepest level, near the origin of the universe, time might not be fundamentally different from space. Time might be spatial. The flowing directional time that we experience might emerge only in certain regimes, not be fundamental to reality. And the origin of the universe might not be an event in time, but a region of space-time where the ordinary laws of physics do not apply in the usual way. But Hawking's approach is speculative. The boundary conditions of the universe, the question of whether time is truly imaginary at the origin, these remain unsettled questions. What is clear is that the Big Bang raises profound puzzles about the origin of time. And the best we can say is that time, as we understand it, began with the Big Bang. Before that, the concept of time does not apply. The end of time. Just as the universe had a beginning, cosmology suggests it will have an end. But the nature of that end depends on which cosmological scenario unfolds. In the expanding universe model, which current observations favor, the universe will expand forever. It will grow colder and more diffuse. Stars will burn out. Black holes will eventually evaporate through Hawking radiation. Protons might decay. Atoms will disintegrate. The universe will approach a state of maximum entropy, in which nothing organized remains. Only a thin gas of particles and radiation, growing ever colder and more sparse. In this scenario, time does not end, but time becomes meaningless. After an incomprehensibly long time, there will be nothing changing. No clocks will be left to measure time. No observers will exist to experience duration. The concept of time becomes empty. An eternal, unchanging universe is, in a sense, timeless. Time is the measure of change. In a universe where nothing changes, time is nothing. In another scenario, perhaps the universe will collapse back in on itself. The expansion will reverse. The universe will contract. Everything will be pulled back to a singularity in a big crunch. Time would end at that singularity, as it began at the Big Bang. In a cyclical universe scenario, the Big Crunch becomes the Big Bang of a new universe. Time ends for one cycle and begins again for the next. Time is not infinite, but cyclical. In yet another scenario, the universe might branch into multiple regions with different properties, and time might behave differently in different regions. Or the universe might be eternal and infinite, with no end. We do not know which scenario is correct. The current evidence favors the eternal expansion scenario, but we cannot be certain. But all of these scenarios raise a similar question. If the universe ends, does time end? If time ends, what does that mean? Does the end of time occur at a particular time? That seems like a contradiction. Or does time simply cease to apply? The end of time might not be an event in time. It might be the cessation of the temporal dimension itself. Just as time did not exist before the Big Bang, time might not exist after the Big Crunch or the heat death. The concept of time is something that applies to a certain kind of universe, one that is dynamic, changing, far from equilibrium. In the early universe and the late universe, in the beginning and the end, time might not apply. And we, conscious beings embedded in the temporal structure of a universe in its middle age, might never fully comprehend what time looks like at the boundaries of existence. Our understanding of time is forever limited by our location in space-time. We are creatures of the middle, living in an era of the universe where time is meaningful and directional. The very existence of conscious, time-perceiving creatures like us might be possible only in this intermediate era. We might be temporally local, unable to understand time from the perspective of the beginning or the end. Time travel's paradoxes. In general relativity, the equations allow for the possibility of closed time-like curves, paths through spacetime that loop back on themselves in time. In other words, the equations allow for time travel. A hypothetical spacecraft could follow a trajectory that brings it back to earlier times. This seems impossible based on everyday experience. Time travel seems paradoxical. If you could go back in time and kill your grandfather before he had children, then your parent would never be born, and you would never exist. But then you could not have gone back in time to kill your grandfather. So you would exist, which means your grandfather was not killed. So you could go back in time. This is the grandfather paradox. It seems like time travel leads to contradictions, and yet the mathematics of general relativity permits it. How can this be? One resolution is the Novikov self-consistency principle. This principle says that events adjust themselves to be self-consistent. If you try to go back in time to kill your grandfather, you will fail. Your gun will jam. You will miss. You will change your mind. Some improbable event will prevent the killing. The universe will protect itself from contradiction. In this scenario, time travel is possible, but you cannot change the past. The past is protected against any changes you might try to make. Whatever you do, the past remains exactly as it was. Another resolution is the many worlds interpretation of time travel. If you go back in time and change something, you do not change your own past. Instead, you create a branching. You end up in a different timeline, one where the past is different. Your original timeline still exists with its original history. You are now in a new timeline. This preserves consistency. Neither you nor the universe experiences any contradiction. Yet another possibility is that time travel is simply impossible, despite what the equations suggest. Perhaps there are quantum effects that prevent the formation of closed time-like curves. Perhaps nature protects itself against time travel through mechanisms we do not yet understand. The physicist Stephen Hawking proposed a chronology protection conjecture, suggesting that the laws of physics prevent time travel to avoid paradoxes. In this view, the equations might allow time travel mathematically, but nature prevents it physically. We do not know which resolution is correct. Perhaps time travel is possible and the universe is self-protecting through the Novikov principle. Perhaps it is possible and many worlds constantly branch. Perhaps it is simply impossible. What is interesting is that the deepest theories of physics do not rule out time travel. They permit it. This suggests that time travel is not logically impossible. It is not inherently contradictory. It is just overwhelmingly improbable with current technology, and perhaps prevented by some unknown law of nature. But at the level of fundamental physics, time is not what common sense suggests. Time can loop. Time can be strange. Time can violate the intuitions we have developed from our limited perspective in the middle of the universe. The paradoxes of time travel are not proofs that time travel is impossible. They are hints that time is more subtle, more strange, more wonderful than we usually imagine. The ultimate mystery. After all this exploration, we arrive at a question that may not have an answer. What is time? Physics describes how time behaves. Physics tells us that time is relative, affected by motion and gravity. Physics tells us that time flows from past to future because of entropy. Physics tells us that time might be emergent rather than fundamental. Physics tells us that time might be a dimension in space-time, or it might be something else entirely. But physics does not tell us what time is. Consciousness describes how time is experienced. Consciousness tells us that we experience a flowing present, a clear distinction between past and future. Consciousness tells us that time is intimately connected to memory, anticipation, and the sense of self. Consciousness tells us that the experience of time can be altered through meditation, drugs, or dreams. But consciousness does not tell us whether the time it experiences is real or illusory. Culture tells us that time is constructed, that different societies experience and value time differently. Culture tells us that time can be cyclical or linear, valued or wasted, colonized by production or freed for leisure. But culture does not tell us whether these are different ways of experiencing a real time or different ways of creating time from whole cloth. And underneath all these perspectives is a fundamental puzzle. The puzzle is this: how can time be a dimension, like space, if we experience time as fundamentally different from space? How can time be objective if it is relative to the observer? How can the future be both open from the perspective of consciousness and fixed from the perspective of physics? How can time emerge from a timeless quantum theory? How can a present moment exist if relativity denies that it is objective? How can conscious beings experience time if time is just a dimension, no different from space? These puzzles are not solved. They are woven into the fabric of our knowledge. They persist despite centuries of investigation by the greatest minds. And perhaps they persist because we are asking the wrong questions. Perhaps time is not something to be explained in terms of something else more fundamental. Perhaps time is one of the fundamental features of reality, irreducible. Perhaps time, consciousness, and reality are not separate things. Perhaps they are aspects of a unity that we do not yet understand. The physicist John Wheeler spoke of the participatory universe. In his view, the universe is not something that exists independently of observation. Rather, the universe and the observer are entangled. Observation participates in creating reality, and consciousness participates in creating time. In this view, the reason we cannot understand time separately from consciousness is that they are not separate. Time is the structure of consciousness. Consciousness is the experience of time. And the universe is neither merely physical nor merely mental, but a participation between the two. This is speculative, but it points toward a reconciliation of the apparently irreconcilable perspectives. Perhaps the deepest answer to the question, what is time, is that time is the medium in which being unfolds. Time is the dimension of becoming, of change, of creation. Time is what allows the universe to be not just a static eternity, but a dynamic unfolding. Time is what allows consciousness to exist as a continuity of experience rather than isolated moments. And consciousness is the universe's way of experiencing its own unfolding in time. We do not know if this is true, but it has a certain elegance. It suggests that time is not an illusion created by limited minds misunderstanding a timeless reality. Rather, time is real. It is fundamental. And consciousness is the universe's way of knowing itself in time. If this is true, then asking what is time is asking what is reality. And the only answer is, time is the answer, watching itself unfold. The gift of finitude. You are going to die. This is not a morbid statement. It is a fact. You are mortal. You have a finite amount of time. And this finitude is, paradoxically, what makes time precious. Imagine a being with infinite time, infinite years stretching ahead. What would motivate this being to do anything? If you have forever, you could always do it tomorrow. You could always defer the important. You could always wait for the perfect moment. But the perfect moment never comes, because there is always tomorrow. A being with infinite time would be paralyzed. It would do nothing, because everything could be done later. Finitude creates urgency. It creates meaning. Because you have limited time, you must choose. You must decide what matters most. You must prioritize. You cannot do everything. You cannot experience everything. You cannot know everyone. You must choose. And in choosing, you create a life that is yours, shaped by your values and your priorities. The philosopher Martin Heidegger called this awareness of finitude authenticity. When you truly confront the fact that you will die, that your time is limited, you are forced to confront who you really are and what you really value. Are you living according to your own values? Or are you living according to what society expects? Are you pursuing what genuinely matters to you? Or are you pursuing what you think you should pursue? Finitude strips away the comfortable illusions. It forces authenticity. And this is not despair. This is liberation. When you accept your finitude, you are liberated from the tyranny of the future. You stop waiting for the right moment. You stop deferring the important. You recognize that the only moment you have is now, and now is enough. The psychologist Irvin Yalom has written extensively about how the awareness of mortality can be therapeutic. People who truly confront their mortality often experience a profound shift. Their priorities change. They focus on relationships instead of possessions. They focus on presence instead of achievement. They focus on being instead of doing. The awareness of death can be liberating. It can give life meaning in a way that nothing else can. In traditional cultures, this awareness was more prevalent. Death was more visible. You lived in closer proximity to it. Plagues, wars, infant mortality, lack of modern medicine, these made death a familiar presence. People could not pretend to have unlimited time. They had to make peace with mortality. But modern culture tries to deny death. We hide it. We age away from it with medical technology. We distract ourselves with entertainment and consumption. We tell ourselves that we will live longer, that aging is optional, that death is something that happens to other people. But this denial comes at a cost. We live with a background anxiety, a sense that time is running out, but that we cannot confront why. We pursue endless achievement, endless consumption, endless distraction, never quite satisfied, never quite fulfilled, because we are not admitting what the hunger really is. We are hungry for meaning. And meaning comes through finitude. Finitude is the gift that makes life precious. It is the gift that makes moments matter. It is the gift that forces us to choose. And it is a gift that none of us can refuse, because finitude is the human condition. We are, all of us, creatures with a finite amount of time. And if we accept this, if we truly accept this, everything changes. Moments that matter. Not all moments are equal. Some moments matter more than others. Some moments stand out, burning themselves into memory, shaping who you become. These are the moments that constitute a life. A moment when you realized you were in love. A moment when you experienced genuine beauty, a sunset, a piece of music, a landscape that took your breath away. A moment when you overcome fear and did something you thought impossible. A moment when someone you loved was in pain and you were there for them. A moment of forgiveness. A moment of being forgiven. A moment when you felt truly alive, fully present, completely engaged. These moments share something. In these moments, clock time disappears. You are not aware of the minutes passing. You are not thinking about what comes next. You are simply present. You are simply experiencing. These moments feel timeless because, in a sense, they are outside of clock time. They are marked by consciousness, not by the clock. A moment of genuine presence can be a single second or a few hours. The clock is irrelevant. What matters is the intensity of presence, the depth of experience. The philosopher and psychologist William James spoke of peak experiences, moments of extraordinary consciousness, of feeling alive in a way that ordinary moments do not achieve. These experiences are rare, but they give shape and meaning to a life. They are the moments that, if you look back on your life at the end, you will think yes, that mattered. The strange thing is that these moments cannot be pursued directly. You cannot plan a peak experience. You cannot schedule authenticity. The moments that matter most are often unexpected, even unwanted. A moment of crisis that forced you to find strength. A loss that taught you what mattered. An encounter with beauty that you stumbled upon. A conversation that happened by accident. These moments have a quality of grace to them. They arrive unbidden. And yet, you can create conditions for them to be more likely. You can be present. You can be open. You can show up for your life rather than just going through the motions. You can pay attention. When you pay attention, you notice the moments that matter. When you are distracted, even profound moments pass unnoticed. A sunset is beautiful whether or not you notice it. But if you do not notice, it might as well not have happened, as far as you are concerned. The practice of presence, of attention, is a practice of making yourself available to the moments that matter. It is a practice of creating time in the deepest sense. Because a life is not measured in hours or days. A life is measured in moments, the moments of presence, of connection, of beauty, of authenticity. These are the moments that are time. These are the moments that make a life. A life. Legacy and continuity. You are going to die, but you are also going to live on. Not literally, though there are those who believe in afterlife, but certainly in the effects you have had, the people you have touched, the changes you have made, the ideas you have spread. You are part of a chain that stretches backward in time and forward in time. Behind you are all your ancestors, stretching back hundreds of thousands of years. Each of them had to survive long enough to have children. Each of them faced their own struggles, made their own choices, lived their own moments that mattered, and they got you here. You are made of their DNA, yes, but also of their struggles, their values, their choices. They are alive in you. And ahead of you are all the people who will come after. Your students, if you teach, your readers, if you write, your friends and colleagues and acquaintances, all of whom are affected by your presence in their lives. The people who are affected by the people who are affected by you. The circles of influence ripple outward in time. Some of these effects will be what you intended, but many will not be. You will influence people in ways you never know. Someone will remember a kind word you said years ago, at a moment when they needed it. Someone will follow a path because you opened a door. Someone will avoid a mistake because you made it and warned them. The effects of your life propagate through time in ways you cannot predict or control. This is the legacy we all leave. It is not always grand, Most people do not change the world, but all people affect other people, and those effects persist across time. Time makes legacy possible. Without time, there would be no before and after, no cause and effect, no influence propagating through generations. Time is what allows your life to matter, not just in the moment, but across generations. The awareness of this can be humbling and liberating. Humbling because you realize how small you are, how brief your moment on Earth. Your 70 or 80 years are a blink in human history, which is itself a blink in cosmic time. You will be forgotten. Your name will disappear. Your great achievements will be dust. Everything you build will crumble. In the end, entropy wins. All order dissolves. And yet, in the time that you have, your life affects others. Your kindness ripples forward. Your wisdom, if you have any, can be transmitted. Your love shapes people. And those people go forward and shape others. The chain continues. You are part of something larger than yourself, something that has been flowing through time since before you were born and will continue after you die. This is what it means to be part of humanity, to be part of history, to be part of the ongoing story of consciousness in the universe. Your small part in this vast story still matters, not because you are special, but because you are here, because you are conscious, because you are alive in this moment, and your choices in this moment affect what comes next. The eternal now. After all this exploration of time, the physics of it, the psychology of it, the culture of it, the philosophy of it, we arrive at something ancient, something that every contemplative tradition has known. The answer to the problem of time is paradoxically to stop trying to solve time and simply be present to the moment. The eternal now. Not the fleeting present moment that comes and goes, but the present moment that is eternal. That is always here. That is all there ever is. When you stop worrying about the past, stop planning for the future, and simply attend to what is happening right now, something shifts. The anxiety that comes from time pressure dissolves. The regret about the past becomes less painful. The fear of the future becomes less urgent. What remains is the present moment. And the present moment, when you are fully in it, when you are fully present to it, is enough. It is everything. The mystics have always known this. In meditation, in prayer, in the practices of contemplative traditions across the world, the goal is to arrive at presence, to be fully here, not to escape from time, but to enter time so completely that the distinction between self and world, observer and observed, dissolves. In that dissolution, time is no longer something happening to you. You are time. Time is happening as you. This is not escapism. This is the deepest engagement with reality. Because reality is not somewhere else. It is not in the future or in the past. It is here. It is now. Every moment contains infinity if you look deeply enough. Every moment contains all the time that has come before. In your body, the atoms were made in stars billions of years ago. In your consciousness, the cumulative evolution of life on Earth is encoded. In your mind, the accumulated wisdom of all of human culture lives. Everything that has ever happened is present in this moment. And everything that will happen is potential in this moment. The Buddhist tradition speaks of Buddha nature, the idea that Buddhahood, enlightenment, the peace that comes from understanding the nature of reality, is not somewhere else you have to get to. It is already here. It is your true nature. You just have to recognize it. Recognition is not about acquiring something you don't have. It is about seeing clearly what you already are. And what you already are is a consciousness arising in this moment, shaped by all of time that has come before, shaping all of time that will come after. When you see this clearly, Time is no longer a problem to be solved. Time is simply what is, and what is perfect. This is not resignation. This is not giving up on trying to improve things, to make the world better, to work toward a future that is more just and more beautiful. Rather, it is working toward that future from a place of presence, from a place of peace, from a place of wholeness. It is acting without attachment to the outcome. It is doing what you can with the time you have, knowing that you cannot control the future, that you can only be fully present to this moment, and let that presence guide your action. The contemplative traditions have much to teach modern people. In a world obsessed with time management, with productivity, with the future, contemplation offers a different path. It offers the possibility of being fully satisfied in the present moment, not satisfied in the sense of complacency, of giving up, but satisfied in the sense of wholeness, of completeness, of being fully alive. This satisfaction does not depend on having more time. It does not depend on accomplishing more or acquiring more. It depends on the quality of presence, and presence is available right now. The meaning of mortality. All of this exploration has been, in some sense, an attempt to understand our own mortality. Because time and death are inseparable. If there were no time, there would be no death. Everything would be eternal, unchanging. But because there is time, we are finite. We are born. We age. We will die. And in this sequence, we find both terror and meaning. The terror is obvious. Death is an ending. It is the cessation of all experience, all sensation, all consciousness, or at least it seems to be. We do not know what comes after, if anything. The uncertainty itself is terrifying. The finality is terrifying. We will lose everyone we love. They will lose us. Everything we build will crumble. Our bodies will decay. Our names will be forgotten. Our books will be unread. Our achievements will be erased. Entropy will win. Everything will return to dust. This is not pleasant to contemplate. And for most of human history, people have sought solace in beliefs about afterlife, about God, about immortality. These beliefs have provided comfort. They have made death bearable. But increasingly, in modern secular societies, people have to confront mortality without these consolations. And in that confrontation, something interesting happens. When you accept your mortality, when you truly accept it, not just intellectually, but in your bones, something shifts. The inevitability of death can be liberating. If you are going to die anyway, you might as well live. You might as well do what you love. You might as well spend time with people you care about. You might as well be authentic. You might as well be present. The acceptance of death is the beginning of freedom. Because once you accept that death is coming, you can stop running from it. You can stop the constant background anxiety and distraction. You can stop trying to distract yourself with endless consumption and entertainment. You can stop the desperate attempt to deny what is true. And in that acceptance, you can begin to live. Not in spite of death, but because of it. The presence of death in time gives life meaning. Without death, life would be infinite and therefore meaningless. Every action could be deferred. Every moment would be like every other moment. There would be no urgency, no passion, no growth. Life would be eternal stasis. But because life is mortal, because time is finite, each moment matters. Each choice matters. The time we have is precious precisely because it is limited. This is the paradox that contemplatives have always known. The awareness of death is not something that makes life worse. It is something that makes life better. It makes life real. It makes life alive. And so, as we conclude this long journey through time, from ancient sundials to atomic clocks, from Newton to Einstein to quantum mechanics, from the rhythms of the body to the machinery of culture, from the deepest questions of physics to physics, to intimate moments of a human life, we arrive at a simple truth. Time is the dimension of life. Time is what makes existence possible, and mortality is not time's enemy. Mortality is time's gift, the gift of finitude, which makes life meaningful, the gift of sequence, which makes narrative possible, the gift of change, which makes growth possible, the gift of death, which makes life precious. We are creatures of time. We live in it. We are shaped by it. We shape it. And in the end, time returns us to the dust from which we came. But in between, in the span of years that is given to us, we have the opportunity to live, to love, to create, to grow, to learn, to connect, to matter. This is what time offers. This is the story of time. And this is your story, unfolding in time, right now, in this moment, which is the only moment that ever actually exists.